Good, good morning, everyone. Well, welcome to AI Inference Infrastructure Summit. Thank all of you who joined the summit. My name is Myung-Jun Lee. I'm principal researcher. We are excited to have a distinguished group of speakers joining us as we dive into some of the most cutting-edge topics in AI ML systems. So before I give the floor to our speakers, I will briefly talk about the background of this summit and introduce some of our efforts briefly. Okay, so we are living at the dawn of AI era, as we all know. AI is not only transforming industries, but also reshaping the very fabric of our daily lives, from revolutionizing the healthcare and transportation to enhancing creativity and problem solving. AI is unlocking the possibilities that were once confined to science fiction, offering the future where the human potential is amplified. AI is already having a profound impact across multiple fields. For instance, recommendation engines on platforms like Netflix and Amazon personalize the contents based on our preferences. GitHub Copilot aids developers by suggesting code, accelerating the software development. ChatGPT and Grammarly assist with the writing from the text generation to the grammar corrections. In computer vision, AI enables self-driving cars to detect and track the object in real time. Face recognition is increasingly used for the secure authentication. AI-powered chatbots and robot advisors are revolutionizing the customer interactions and transforming how we manage finances. So these are just a few examples of how AI is dramatically transforming industries and our everyday lives. So with the explosive growth of AI use cases and the services, the demands on the AI infrastructure have skyrocketed. NVIDIA reported shipping 3.76 million data center GPUs in 2023 alone. This year, the big tech companies are investing heavily to strengthen their AI infrastructure, fueling an increasingly competitive race for the AI dominance. The push for the AI infrastructure also extends to the government policy. The US government recently announced the Stargate project, a groundbreaking initiative with the $500 billion investments to build a state-of-the-art AI infrastructure. While these AI infrastructures support both training and serving, today we will focus on the serving side, as model serving comes with its own set of challenges and significant costs. While the training AI model presents its own set of challenges, AI serving introduces an entirely different set of complex and demanding issues. First, model deployment environment can be highly heterogeneous with the various types of accelerators, devices in use. These differences affect the key aspect of deployment, such as GPU or GPU memory, computation efficiency, and communication overhead. On top of this, the diverse application requirements add another layer of complexity. Some AI applications are latency sensitive, like chatbots or the autonomous driving cars, while others, like medical diagnosis and fraud detection, require extremely high prediction accuracy. Adding to this challenge are the multimodal models, which increase the complexity even further. Different modalities such as text, image, sound, video have varying computational and memory requirements. The mix of these inputs and the tasks can impact the overall infrastructure utilization and the application's performance, as different tasks need different resources and amount. Finally, AI model serving isn't just about managing the model itself. AI serving toolchain is also becoming increasingly complex. Dependencies and interactions between the model and the supporting tools can create a potential bottlenecks, impacting the overall efficiency and the utilization of the infrastructures, also affecting the application's performance too. So given all these challenges, efficiently utilizing the expensive AI infrastructure is a crucial but a complex research problem. Okay. To recognize the importance of this research topic, let's quickly go over some exciting current project in AI serving that we work with research, the academia. Aditya Akella at the UT Austin is working on the scalable LLM inference with a focus on the efficiency and the maintainability. Neeraja Yadwadkar, also from the UT Austin, aims to create a cost-efficient distributed inference serving by automating the deployment configurations for the massive LLMs. Alexey Tumanov from the Georgia Tech is developing elastic LLM serving solutions that balance efficiency and accuracy using stitch nets. Kevin Leo and Nat Shroff at Ohio State University are building a fault-resilient and efficient scheduling algorithms for distributed machine learning inference jobs. Finally, Morshaf Chaudhry from the University of Michigan, who couldn't actually join the summit because of a personal commitment, is researching the multimodal inference with the goal of creating an efficient the framework for the multimodal modal serving. These projects are tackling the core challenges in AI serving to make it more scalable and efficient. Many of the PIs of these projects are today here as our speakers, so they can talk more about their research later. Okay, we are also making our own efforts. ImpScale and Multiworld are the project led by the Cisco Research. The goal of these projects is to enable elastic scaling of model serving based on the real-time demand changes. ImpScale is in an ML serving system that is fault resilient and offers efficient auto-scaling functionality out of many other functions it can offer. Multiworld is the elastic collective communication library that extends the nickel and glue on top of PyTorch. And this is a building block for the ImpScale. And the library allows for the flexible control of collective communication groups. Therefore, even if one group fails, still it can allow the communication of surviving the workers. We open sourced this project. You can find the details from the link here. And also we published a technical photo on archive. You can actually check it out too. So let's dive slightly into the question of how to elastically scale the models in response to the real-time demand changes. Okay. So to start off, let's take a look at how one can deploy a large model. I will use the simple data plus the pipeline parallelism as an example. Here's a large model is partitioned into smaller pieces called stages or the blocks. Each stage is run on one GPU. We can have a more replicated pipelines to improve throughput. We can deploy it statically or dynamically. One key issue is resource underutilization. Request rate can change over time. The deployment to meet the peak demand can lead to the over-provisioning and underutilization of the expensive GPU resources. Of course, we can actually deploy this pipeline dynamically, but deploying the dynamic can take long. Therefore, you can actually affect the performance of the applications too. So another issue with this approach is that one stage failure can lead to the failure of entire pipeline. This can cause the serving capacity degradation, and reconfiguring the faulty pipeline can take a longer time. So which affect availability. Probably our vision is to scale the stages independently. For instance, let's assume that the stage 2 is a performance bottleneck. This can be because stage was deployed in a slower heterogeneous hardware, or the stage may need to conduct a heavier computation than other stages. So in such a case, we can improve throughput by the replicating a bottleneck stage. If the stage 2 is still the bottleneck, even after the replication, we can continue to deploy more replicas for that stage. As we deploy more, the bottleneck stage can be moved into another stage, just like the microservice systems, where we can scale out the different microservice component independently. Our vision with the ImpScale is to scale out each stage independently without losing performance. Okay. In other words, in other words, gradual increase in resource usage is possible while meeting the demands. Also, in order to meet the request demands, we don't need to use the homogeneous hardware. If the performance is profiled against the different hardware types, we can pick an appropriate hardware type that can meet the incoming requests. Finally, single stage failure only to the complete failure of a pipeline, as long as one replica per stage is presented. If a bottleneck stage isn't lost, then the capacity of this approach can provide a higher capacity or the throughput than the naive approach. So achieving the vision involves several key research questions. I will just talk a little bit about some of these. We first need to accurately profile the model and its infrastructure to break it into manageable components. Deployment must consider the factors like throughput, latency, available resources, with the challenge being that the model split and the deployments are closely connected. And we must dynamically route the request to maximize resource utilization and performance, adjusting to factors like task types and the demands rate. Okay. So I will skip the rest of the other questions, but in short, these questions highlight some of the challenges of AI serving models effectively, ensuring the scalability and performance in a dynamic environment. We are actively conducting the research to answer these questions. Okay. So without further ado, let's dive into the exciting talks that our speakers prepared today. Today, we have 4 amazing speakers. Each talk is 30 minutes long, and the last 5 minutes of each talk can be dedicated for the Q&A. And at the end of talk, they will conclude the event with a roundtable panel discussion where our speakers will answer your questions and engage in a deeper conversation on these exciting topics. We hope you enjoy the event and have an engaging time today. So first, we will start with a fascinating talk on the systems for the adaptive inference by the Aditya Akella from the University of Texas at Austin. Aditya, floor is yours.
Thanks, Myungjin. Let me share my screen. Okay, is the screen visible?
Yes.
All right, cool. Okay, thank you everyone, and thanks for giving me this opportunity to present our work on adaptive LLM inference systems. I'm Aditya Akella from the University of Texas at Austin. Some of this work actually echoes many of the points that Myungjin brought up in his introduction about the challenges in inference systems and the ideas that are being explored to overcome those challenges. So maybe a bit of this will be a recap, but I want to take a slightly different approach to how we build adaptation into inference. Okay. So, I think it's basically something that we all understand. There's a rapid expansion and use cases of large language models across various sectors. There are various technical use cases like automation, creation of content, security, analytics, but also sort of a variety of domain-specific use cases such as personalized learning and education, healthcare, increasingly also used in research and mathematical exploration, for instance, and software adoption. And also many of these use cases often overlap. For example, healthcare can integrate research and personalized learning. And so there is a strong interconnected and evolving nature of the use cases for LLMs here. This actually brings a lot of the spotlight to how well we support inference and in order to make sure that these applications that I listed on the previous slide run well, right? So there are at least 3 key considerations for inference to support these applications: speed, accuracy, and efficiency. Speed emphasizes the need for real-time output in many cases, where you want inference to produce tokens at timescales that are of human timescales or potentially even faster, especially if you're part of an automation pipeline. Accuracy, like Myungjin mentioned, many of these applications impact decision-making. especially in something like healthcare, or even in some of the human-facing LLM use cases, accuracy of responses matters a lot. And efficiency basically addresses the point that inference can impose high costs, and there's a high energy footprint of AI accelerators, and so ensuring inference is efficient also really matters a lot, right? Now let's take a quick look at sort of what makes inference challenging, sort of making some of the points that Ming-Jin brought up, but from a quantitative point of view. First, this is a trace that was released by Azure. Many inference serving systems see unpredictable spikes in workload, and this makes, at the very least, planning for how to provision resources to support inference extremely challenging. Secondly, if you look at how resources are exercised by the requests that are being served by an inference node, there can be a lot of variability both temporally and spatially. And also the resource requirements themselves can be extremely large, tens or few hundred gigabytes of memory, for instance, in this case, that is used, not to count the amount of processing that GPUs would require for supporting inference in examples like this, right? These systems also see a lot of fluctuation. The requests can have varying number of tokens in them, and for requests and then their responses, the sizes of the responses in terms of the number of tokens can also vary drastically. And again, these are measurements taken from some recent papers. You can find the links to those papers on the slide here. This paper actually goes into a lot of details into how variable the sizes of requests can be, and there are differences between, for example, how ChatGPT handles this versus Llama, and different architectures can have quite a few sets of nuances in the variability of these sizes. And also just the number of use cases, again, reiterating the point that Ming-Jin made, is very diverse. And even in a particular application like chatbots, the prompts can be of very complex and diverse nature. They can have very long context lengths or very short context length and expect responses of equally diverse complexity. The claim is that amidst all of these very challenging aspects of inference workloads, and also these challenges are rapidly evolving, today's inference systems are incapable of supporting inference while optimizing speed in terms of how quickly responses are received, ensuring accuracy, and meeting efficient inference goals. And I claim that the main reason for this is fundamental rigidity underlying the design and operation of these inference systems. So let's take a look at sort of what inference systems look like. Typically, there is some sort of a scheduler. You get requests. These are prompts from users. Those the scheduler farms those requests out to machines, where on a GPU, there may be a model sitting, and on the CPU, there are other variants of the model. And of course, this is an oversimplified picture. Like Ming-Jin showed, many of these models may spread multiple GPUs and multiple machines. So this is a very simple picture, right? Typically, when the load increases, many existing serving systems often tend to drop requests because they overflow the local memory and they overflow the computational capacity. And to mitigate this, many LLM providers use this approach where they, under request loads, they would downgrade to a weaker model. So, for example, you may switch from a Llama 13B to a 1.1 billion model in order to meet resource demands. So I'm going to call this approach model level control. And this is typically done because it's infeasible to have multiple machines that all host the largest models. And it also takes a lot of time to spin additional machines with these larger models. Now, the problem with this kind of model level approach is, at the lowest level, even though I show a smaller bottom model being loaded into the GPU memory, there are prior requests that are continuing to run. So they continue to use the older models. So there is memory bloat, and this tends to worsen memory scarcity. And it also forces us to use small batches, which reduces the efficiency of inference. But more importantly, the existing approach of basically doing this model level switching induces a more fundamental trade-off between accuracy and resource use. In particular, as you can see on this picture, you may have a very small number of model variants with very rigid resource footprints in terms of the memories that they use versus the accuracy that they provide for requests that they're serving. And there are also very coarse trade-offs in terms of other metrics, for example, how expensive it is, the time to first token, and the way they deal with various downstream tasks. Okay, so why is there this kind of rigidity? And how do we think about this rigidity? What I want to argue is that in existing systems, the way they execute requests has two attributes. One is coarseness, and the other, what I call early binding. What I mean by this is that whenever, like I showed on the example earlier, whenever there's a spike in load, it triggers a switch in the model that you use. You fall down, you degrade from a high fidelity model to a low fidelity model. And from that point on, every incoming request into the system uses the same lower fidelity model. Also, the moment a request is queued at the scheduler, the entire set of attributes of that request's execution until responses are received are bound at the time the request arrives into the system. And what this means is that this tends to tie up system resources in a very rigid and specific fashion in serving any given request. And this is worsened, and these attributes are worsened by the aspects of LLM inference workloads that I showed, their heavy resource requirements, their extremely spiky nature, and so on. Okay. So the question is, how do we build inference systems that break out of these coarseness and early binding and enable more flexible traversal of the trade-off space between speed, accuracy, and efficiency? So that's the question that we've been seeking. And the main insight that we have been going after in building such systems is by inducing flexibility via this approach of decoupling semantics from implementation across the stack. So let me explain what I mean by this. So there are at least two aspects where this decoupling can be looked at. One is at the level of the model, and the other is at the level of the input. So when you look at the input, there is this notion of what the user requested. There is a certain prompt that the user provided to the LLM. And the model is essentially serving the purpose of analyzing the prompt and coming up with a response. So the model is serving the goal of, what do we need this prompt and how do we process this prompt, and what does the prompt expect in return? So this is what I mean by the semantics, right? So there is something we expect from the model to generate content or to provide more context or what have you, and the input is what the prompt was. What I mean by implementation is how these things are done. For example, in the case of input, there may be various ways of representing the actual input that the user provided, the specific prompt, for instance. And similarly for the model, what I mean by this is exactly what model you use to serve a particular user's request. Now, why is this distinction important? Typically, the top level, the semantics is unique. It is tied to the request and it is tied to the intent of the request, right? However, the implementation offers many options. There may be multiple different ways of representing inputs. You can sparsify the inputs. You can do various other kinds of modulations or changes to the input. And similarly, there may be multiple different ways of exercising models to serve the intended purpose of the input request. Okay, so while semantics is unique, these bottom level implementation options there are many such options. So what this insight leads us to is building systems that enable what I call fine-grained late binding as opposed to coarse-grained early binding in inference systems. What this means is that given the semantics of requests that are coming into the system, you delay as much as possible the specific implementation details, and you make those choices at runtime as the request is executing. And by this, I mean the semantics are what the model is going to do to a particular request, and the implementation is all of these green box details. What this allows us to do is to take a request's processing and logically split it into smaller pieces. And each of these smaller pieces or portions match the current progress of the request with the overall state of the inference system and how closely we are progressing towards the goals we want to meet for the request or for the overall system. And at each state, tailoring the resources that are available, the memory, the computation, and so on, to the specific request and its needs, as well as the overall system's needs. And by enabling this kind of fine-grained approach, you can improve the execution flexibility, both at the level of individual requests, but also end-to-end. And what I think this kind of an approach will give is a much greater variety of points in the intermediate space on the accuracy versus resource spectrum. This is just one example, but there may be many other points that provide intermediate resource footprints and accuracy needs, as opposed to these rigid choices. And I argue that this kind of a late binding and fine-grained approach, in addition to the fact that it gives this flexibility, is actually going to be crucial as we go towards things like agentic AI systems, where there is a lot of unpredictability given a particular prompt or a workflow that you're trying to realize end to end. Exactly what resources do I need? I don't know at the time the requests arrive into my system. Some of these can be extremely long-standing and run for a very long period of time. I also feel that this kind of an approach is extremely crucial as inference moves away from dedicated resources to operating in situations where there are resource constraints, for example, in multi-tenant clouds, or doing inference over spot instances, or at the edge, for instance, where there is a heavy degree of contention. Okay. So what this talk I want to do in the rest of this talk very quickly is give you some examples of how we can leverage fine-grained late binding by introducing this flexibility at the level of the model and at the level of the input. I'm going to talk about two works, but we have done a few other things that I won't be able to get to here. And in both of these works, I'm going to spend more time on the model side than on the input side. But I want to place the emphasis on the fact that there are novel choices that enable these flexible choices. But also, it's not just the fact that these choices exist. There is also novelty in the ways you can leverage these different choices. Okay. So let's move on. So the first part is, how do we introduce flexibility into the model layer, right? So the approach that we have looked at, and this is a paper under submission, is that if you look at attention, which is kind of like the basis of many of these large language model, it's very expensive. It has a quadratic computational cost and significant amount of memory footprint. But of course, it is great in terms of the accuracy that it serves for various end-to-end purposes. But in recent years, we've seen things like linear attention approaches and state space models that offer a promising alternative to self-attention by both reducing computation from quadratic to linear and also making memory usage a constant, right? The main challenge, though, is that these tend to weaken the notion of attention, and as a result, they struggle with accuracy. And they try to capture global token relationships using fixed size hidden states, and this creates a bottleneck of sort in terms of how accurate these models perform. Whereas self-attention looks at all pairwise dependencies between different applications, between different tokens in a prompt, right? And there have been many recent approaches, like Mamba is one approach of a state space model and gated linear attention that have kind of shown some of these trade-offs that systems, these more recent alternatives to transformers can induce. So what we are proposing in our adaptive inference system is one that leverages the capabilities of these alternate models, linear attention and things like state space models, when the system enters heavy load or when there is heavy memory pressure. So what our approach does is it's going to distill self-attention layers into what we call dual state linear attention layers using a knowledge distillation approach. So what we do is before deployment, we train our DSLA layers from transformers to enable sort of on-the-fly conversion of self-attention layers to these lower cost linear attention layers that have linear computation and constant memory, and do this at the time of inference. And of course, while we are converting more and more layers, it's going to save resources. It also degrades performance. So in order to balance the efficiency we get from accuracy, we're going to apply this layer-wise distillation approach, replacing layers only as needed. All right, so let me actually introduce very briefly what this dual state linear attention model is and how we optimize it. Okay. So the DSLA model, or dual state linear attention, it is designed to address some of the drawbacks of linear attention models and bring their capability closer to transformers. So what gated linear attention models do, as shown on the bottom, is that they are very good at paying attention to recent tokens. And this is typically because they operate in this linear state update model. The hidden state updates in a sort of almost like an exponentially weighted moving average fashion. So they tend to pay a lot of attention to recent tokens, whereas transformers pay attention to tokens across the entire spectrum of an input prompt. So in order to mitigate this, what we do in DSLA is we introduce an additional states. This is why we call it a dual state linear model. And we train the model using a contrastive loss on the cosine similarity between the two states that forces one state to look at recent models and the other state to look at historical information. So that's what you see in the purple lines. One model looks at recent information, whereas the other model, which is trained contrastively, looks at historical information. So what we get with this is try to meet as much as possible, emulate the ability of the transformer to do pairwise attention across tokens. Okay, so that's a very quick overview. The DSLA model, the way we do it, employ it in an inference system is as follows. So this basically shows, our serving system handling a large token length prompt. And suppose there is a spike in the system load. In fact, when there is sort of moderate load in the system, we continue to use self-attention across all of our layers for full accuracy. But when demand and resource pressure surges, what we do is to dynamically replace the less sensitive layers in the self-attention part of our decoder with DSLA layers. And what this does is it dynamically reduces the resource usage while preserving performance as much as possible. Okay. So this is a very high level overview of what we do in our DSLA serve system. Let me give you a quick sense of some of the benefits that we get from using this. So we evaluated this on a long context benchmark, and we compared the DSLA model where we convert 25% or 50% of transformers self-attention layers into our linear layers for the Llama 2 7 billion model. And that essentially serves as the teacher model from which we distill our linear models. Okay. We also compare against other gated linear attention model and Mamba and Zamba, which is a hybrid of self-attention and state space models. So what we find in our results is that our approach significantly improves the performance in sort of multi-doc QA type of workloads and few short learning tasks compared to the teacher model. And basically this shows the effectiveness of linear attention for kind of long context understanding. We also find that our approach outperforms these hybrid models such as Zamba across multiple tasks, including multi-document Q&A, code understanding, and some of the few short learning tasks, right? In fact, the most notable thing is that DSLA surpasses both Mamba and GLA in all of the long context tasks while maintaining very low fine-tuning cost compared to these other models. Another quick view on some of the latency benefits we obtain. Here we compare the prefill and decode latencies of our models with 25% and 50% of the converted layers against a baseline transformer. On the left, we see that if we are using fewer than 4K tokens, transformers are faster because DSLA's linear projections are not trivial. They do take some cost. But once we cross 4K tokens, DSLA tends to outperform because it has better GPU memory bandwidth use efficiency. In terms of decoding, the transformer tends to slow down as the number of output generated tokens grows, whereas others have better linear scaling. And the more you convert, the better the scaling tends to get. The other interesting point to notice from this figure is the spikes that I show here. And the point to notice that is interesting is that transformers have a lot of spikes, whereas for the converted layers, we have fewer spikes. Essentially, what's happening here is that the CUDA malloc function takes a lot of time, and it can take up to 300 milliseconds to up to a second to do mallocs. Whereas because we don't have as much memory pressure, we see far fewer spikes in our converted layers.
Okay, Aditya, we have a few questions from the audience.
Yeah,
Let me
absolutely.
just,
Go for it.
yeah.
I'm happy to take them.
So I'll just read. Given the challenges of coarse and early binding in inference workload, do you see the mixture of expert as a viable solution to improve dynamic scheduling and the resource allocation? If so, what are the trade-offs when implementing MOE in production?
So that's a great question. I'll give a brief answer. We can take it more detailed towards the end. MOE is a particularly challenging type of a workload. In particular, because with MOE, the way the router works is that you don't really know which experts are going to be needed until you exercise the router at each layer. And actually, that's kind of not really great, even though the decision is happening late, because you don't know what that decision is. You can't really plan for everything ahead of time, and you don't have a whole lot of time to plan. So MOE is interesting, and it is a challenging workload to optimize for. However, one thing I'll note is that in our recent work that appeared in ICML last year, we showed that for many MOE models, the set of experts that are loaded on across a set of layers can be estimated ahead of time at the time the request arrives. So you don't need to invoke the router at every time. You actually can pre-decide what the router ought to do. And that gives us a lot of flexibility. You can load all of the experts at time. So in the case of MOE, there are challenges, but they can be overcome. In order to overcome that, we kind of have to somewhat change the MOE architecture. And with that change, we can achieve better benefits. But whether MOE is an actual answer to this is a deeper question, but I'm happy to take that again. Should more comments arise at the end.
Yeah, I have two more questions. Are different layers distilled for the different prompts, or not?
So yes, so actually what we find is that a lot of it depends on the workloads. So for some of the more difficult tasks, we end up preserving most of the self-attention and distill only the latter layers in our decoder. But some of the simpler tasks and also situations where the prompt lengths are large, indicating a simpler task, we tend to distill some of the earlier layers. It's interesting because, especially if you think about context length, large context length also means a lot of memory. And that's the case where we end up also starting to distill earlier, leading to this compounded resource use benefit for us. So yes, the answer is yes, but it also provides a lot of interesting opportunities in this design space of deciding when and what to distill.
Okay, so I can probably ask one more, and then I'll let you proceed. Can you actually swap the new attention, the DSLA layers, with the original self-attention layers in any model, or do we need to do this in a new distilled model?
So what we have done is we have taken an existing Llama model, and in a pre-training step, we have created these distilled layers. So in theory, you can take any of these models and on the fly load these distilled layers for them. I don't know if that answers the question that was asked.
Yeah.
In other words, it doesn't have to be a new model that you develop for this.
Okay, thank you. Yeah, so time check. We have around 7 minutes left or so.
Okay, so I mean, again, so this we saw. So in terms of end-to-end improvements, this is just a quick. Let me just quickly go over this. Just summarize this. We see that with this conversion rate, we can get actually pretty significant improvement in latency, and these show for various sequences, depending on the sequence length, how aggressively we convert. And as I said earlier, as the sequence length grows, we tend to convert more aggressively because we have more context, and that allows for more approximation in the processing of the request. All right. So I don't have a whole lot of time left. So, and I want to spend time answering questions. So the second part is actually how do we do this by modulating the input? And here the idea is we can actually be selective about how we process an input. And this is particularly in the context of multimodal models, This is actually work we did in collaboration with Neeraja, who will be speaking later today. The idea here is that we can optimize at the input level by selecting a subset of modalities in these multimodal set of constraint models. And the reason we came up on this insight was that if you look at the multimodal models, not all modalities are necessary to achieve the highest possible accuracy. So these graphs here show accuracy on the bottom right and the combinations of different modalities. And as you can see, in many cases, you can drop one or more modalities and achieve the same, roughly the same overall accuracy as as using all of the modalities in the input. And this kind of makes sense because there's a lot of redundancy in the information encoded. It also depends on, for example, what the video is showing. Is it a rapidly changing scene versus a scene that is staying constant? So what we do in this approach in Moselle is we profile these different modalities in terms of the accuracy they induce and the latency they incur. And we maintain an offline table of these trade-offs between accuracies and latencies. And in an online stage, given a batch of requests, we profile what modalities to use to each of these requests so that we achieve a target minimum accuracy while also meeting latency SLOs. I'm sorry that I won't be able to spend too much time going into this, but hopefully at a high level, it makes sense as to what we are doing. We have two stages. We do this offline profiling, and online, we kind of take a batch of requests and do surgery on them, deciding what to drop to meet SLO and accuracy goals. Quick overview of the results. We are able to maintain high throughput while also minimizing the SLO violation rate. This paper was published at EMNLB last year. Happy to share a draft if people are interested in more details. So actually, this is the end of my talk. What we are doing right now is looking more algorithmically as to what these choices are. This is a question that came up earlier. Does MOE provide more options? What are these algorithmic options? What kind of options can we apply at the input layer? Are there other ways of sparsifying inputs, or do we employ an out-of-the-bag tokenizer for all inputs? And how do we leverage these choices? I showed you a particular way of changing the inputs and planning, and I showed you a particular way of leveraging self-attention versus linear attention. But is there a more systematic framework? Is there a way of doing end-to-end planning and a way of specifying what we want and automatically deriving the way of leveraging these choices at execution time? Also, beyond model and input, are there other avenues for this flexibility? Are there avenues in the way we schedule some of the requests? And I think Alexey may talk about some of this stuff in his talk. Can we do this at the collective layer and so on? So right now we're kind of putting all of these pieces together and building an end-to-end inference stack that enables this kind of adaptation, targeting things like agentic AI systems in the future, and also inference in spot market workplaces. All right, so I'm going to end here and see if there are any other questions. And I apologize if I went over time.
So let's wait. Okay, so just in case since there's no question, I can actually quickly ask one more question about the DSLA.
Yeah.
So, in order to run the DSLA and as well as the self-attention for serving the requests, do you actually need to keep both of them in the GPU memory? And does it actually incur the extra, memory or pressure or the footprints? How do you actually, is that some sort of a trade-off that you have to
so
make?
what we do is we store them in host memory and load them from host memory, load the DSLA models from host memory onto GPU as, so it does take more memory bandwidth, right, in order to load the model. But we save in terms of the memory pressure that is induced for attention computation. The quadratic memory and the multiple passes that you do in computing memory, those things are saved. And in effect, you come in front when using DSLA models.
Okay, that makes sense. One more, small question is, do you plan to actually make the system open source?
Yeah. So we are in the process of doing that. Moselle is already on GitHub, the input modulation work. The DSLA, it should be released open source in a couple of weeks. We are just polishing up the work.
Okay, then we can probably follow up to get the the open source link. Okay, great. Thank you. Thank you for the great talk. So our next speaker is the Rachee Singh from the Cornell University. She will be talking about fantastic topic, slightly different from the what Aditya actually talked about. The title is Programmable Chip-to-Chip Photonic Fabrics in the Multi-Accelerator Servers for ML. Rachee, go ahead.
Okay, can folks hear me?
Yes.
And can folks see my screen?
Yes.
Okay, great. Hi, everybody. I'm Rachee. I am an assistant professor of computer science at Cornell, and I'm super thankful to be here. And it's great to be following my presentation after Aditya and Myungjin have already presented. So the good thing is I don't have to give you a background. You're pretty primed for why we are looking at a challenging problem when we talk about inference for large machine learning models. Okay, but my talk hopefully is going to convince you that we need a radically different way to design multi-accelerator servers that are the workhorses for these machine learning workloads. Okay, the talk actually builds off of multiple papers. I've listed them up here. They are there on my website. If you can't find them, let me know and I'll send you drafts. But to begin, I want to first thank the group. So at Cornell, I lead the Systems for Photonics group, and these are the wonderful folks who have made this research happen. So if you think of good stuff about this work, think about them. The bad stuff, I'll take the blame for. Okay, so let's dive right into it. What are multi-GPU, multi-XPU, multi-accelerator servers? Okay, these servers are basically workhorses for modern ML jobs. These are the hardware targets on which you are training and inferring on your models. And typically they look like the following. You have about 8 XPUs or fewer on the board of a single server. And between these XPUs, you have some electrical connections. These are high bandwidth electrical interconnects, and different companies have different interconnects that they swear by. For example, you might be familiar with NVIDIA's NVLinks and NV switches based interconnect. Similarly, Google has an interchip interconnect, or ICI. So basically, a multi-accelerator server consists of these handful of accelerators on the board of a server connected with a very high density interconnect. Okay. And when you think about how these are sort of the building blocks of large ML clusters and data centers, it looks something like this. So you can imagine that a rack in a data center consists of multiple of these multi-accelerator servers. You have multiple racks in the data center, and these racks all together connect to some sort of a data center fabric that provides connectivity between these racks. And there are very many different kinds of data center fabrics that have been proposed by different researchers. The more traditional cloth fabrics are we've known about them for decades now, and more recently we've seen data center fabrics that are direct connect. So there's less packet switching, more circuit switching going on there, and they form what is called a torus. So the TPU data center fabric notably is a direct connect torus topology. Okay, so now I want to highlight something that's a problem with these multi-accelerator servers. We already know that models are too large for them to fit within a single accelerator. As a result, even during inference, we need to distribute the computation across multiple accelerators on the board of a single server or across multiple multi-accelerator servers. When you do that, when you distribute computation across multiple accelerator, the communication then is on the critical path of whatever that job's throughput is. It might be tokens per second, it might be, what have you. That ML throughput depends on the performance of the interconnect between accelerators. And what's very interesting is that researchers have found the existence of what is the interconnect bandwidth wall. And I'm showing you a graph that's borrowed from this IEEE Micro 2024 paper that says accelerator flops are scaling at a higher rate than the rate at which bandwidth between the accelerators on the same server is increasing. And the problem with that is this is going to lead to a disparity in the sense that accelerators are going to sit idle waiting for communication to finish. And there's already a bunch of work that talks about how this is a problem, how expensive and energy consuming accelerators are sitting idle. Okay. So the question that we will try to answer in this talk is how can we sort of break this interconnect bandwidth wall? How can we scale the XPU to XPU bandwidth in modern multi-accelerator servers for machine learning? So I'm going to propose something somewhat radical. I'm proposing that let's replace the electrical GPU to GPU connections or XPU to XPU connections on the board of a server with a photonic or an optical interconnect. Let me first show you what this might look like logically, and then I'll show you a photograph of a prototype. So imagine you have this server scale photonic interconnect. This is sort of like this substrate on top of which you're going to stack your GPUs. Let's see what that looks like. This is my server scale photonic interconnect. It's divided into what I'm going to call tiles. These are sort of physical locations on the interconnect. So tile 1, tile 2. And you can imagine that the XPU is stacked on top of this tile in this manner. And the key difference that this design provides compared to what we already have is that these connections between accelerator, these green links that you see, are optical connections. These are photonic. This is exactly what the server scale photonic interconnect is providing. And I'll show you a whole bunch of pictures of an end-to-end prototype, but this photonic interconnect itself, there's a photograph of a prototype of this that was fabricated in Global Foundries by our collaborators. And I'm going to show you that on the right side. But if I was to show you sort of the vertical cross-section of what this multi-accelerator server might look like, you can see there's the photonic interconnect at the bottom, and on top of that, you've stacked accelerators that communicate using optics that this interconnect is providing. Let's dig deeper. What is the architecture? What is it that this is really giving us? Let's just zoom into that server scale photonic interconnect, the gray box from the previous slide. And I'm going to show you again those tiles that I was telling you, which are physical locations on this interconnect. So tile 1, 2, 3, and 4. And on each tile of this interconnect, you have what are called transmit-receive blocks. And these are very similar. I mean, I know I'm giving this talk at Cisco, so you guys are very familiar with the idea of transponders. These are exactly those boxes. These are transmit-receive boxes, but now they are on this server-scale photonic interconnect. And imagine you have multiple of these TXRX blocks in each tile. I'm only showing 3 here. And that accelerator that I was showing you stacked on top of the tile is actually talking through these TXRX blocks. The main thing that we want to focus on is the connectivity between these TXRX blocks on the photonic interconnect is enabled by what are called optical waveguides. So forget your copper traces. We're not talking about these optical connections that are sort of etched on this photonic fabric. Okay, so this is the simplified view. You are getting connectivity through this photonic interconnect, and accelerators are sort of sitting on top of it. There's one catch, one simplification that I made, which is kind of critical. So let's kind of dig deeper a little bit. Those waveguides that I was showing you, the black lines on the interconnect, they actually have physically, they have these switches that they connect to. So on this interconnect, I've got these switches. And imagine this switch looks like the one that you see at the bottom. It's a 1x3 switch that is programmable. It's a programmable optical 1x3 switch. And imagine every waveguide is connecting to multiple of these switches. So you could imagine you take one switch and it can actually be cascaded with a bunch of other switches to form what is a dense photonic fabric on the interconnect. And I'm going to show you this at scale, I'm just going to take that 4-switch structure and represent it using that diamond shape that you see on the right side. Let's see what this looks like. Now, on this interconnect, which had these transmit-receive blocks, you're forming this fabric with waveguides as well as these 1x3 switches that are forming those diamond structures. And they are everywhere on the server scale interconnect that we are using. Okay? So now the cool thing that you can do once you have a programmable switch, a fabric on this interconnect, is you can on-demand program end-to-end optical circuits between accelerators that are inside the server. Let's see what that looks like. you can program this circuit between tile 1 and tile 2 and essentially enable connectivity that's contention-free and all optical between accelerators that are sitting on top of those two tiles. Okay. Similarly, you could connect tile 2 and 3, you could connect tile 3 and 4, and yet another cool thing about this is because these silicon photonic waveguides are so tiny, they only take a few nanometers, you can have thousands and thousands of them on a single interconnect that of this scale. Okay, so I'm going to show you some experimental insights about a test bed that we have in the lab. And this test bed, you can see a photograph of this on the left. This is the lab hardware prototype. And using this prototype, we were able to show that you can create optical circuits between accelerators in something close to 3.7 microseconds. And while I'm not showing results for the loss here, we do have papers that report the loss. All of this can be done with significantly low loss. Okay, so what this capability gives us is the ability to form circuits between accelerators in the same server that are all optical and that eliminate contention by design. And we can do this relatively fast. I know that 3.7 microseconds is not something that we can just forget about. It's a significant delay, but it's reasonably fast. So what does this give us? In addition to the high bandwidth that optics brings, what does this unlock for us? And for the rest of the talk, I'm going to tell you that we leverage the programmability of this photonic fabric to unlock, first of all, just optimal bandwidth between accelerators. So it's contention-free. It's really the best you can get in terms of the egress bandwidth of the accelerator. And you can unlock fault tolerance in large-scale ML deployments. And I'll show you through examples how this works before proceeding to show you end-to-end results of what we've done. Okay, so this is our system that's called Morphlux. Let's see how Morphlux does this. I'm going to show you two examples that hopefully motivate the idea. Let's get back to that, that design we started off with at the beginning of the talk, where we have a bunch of these racks with multi-accelerator servers. And I told you that they connect up to some kind of a data center fabric. Okay. In some of the more recent ML-centric data centers, this fabric is optically circuit switched already. So I want you to sort of differentiate these two ideas. There's already photonics in a whole bunch of other places in the data center. What I'm proposing is we should bring it essentially to the last mile, which is on the board of the server between accelerators. Okay, so that was just to refresh your memory. Now, in these ML-centric data centers, let's see what connectivity looks like. I'm not going to make it three-dimensional. Let's just look at it in 2D. We've got 4 servers here. Each of these 4 servers have 4 XPUs on the board of a server. So you can imagine this is something like the TPU design. And in this design, this is the state of the art. All of the black links that go between XPUs are electrical. Okay, so you can imagine this is the connectivity within the rack of any of these ML-centric data centers. Okay, now you've got this, and let's say these are all multi-tenanted situations. So you can imagine, let's say there's one tenant, that's you. You carve out a portion of 2 servers, that's 8 XPUs for an inference job that you plan to run. And I'm tenant 2, I carve out other 8 XPUs in this manner, and we both essentially have a different set of XPUs that we are using for our fine-tuning inference jobs. Okay. Now, something I want you to focus on. Let's look at one specific XPU in this design. Okay, any one XPU. If you look at it carefully, in this electrical design, the one that is the state of the art, the egress bandwidth or the escape bandwidth, if you like to call it that, from any accelerator is statically partitioned along 3 directions here, right? This, if you imagine this in 3 dimensions, you would actually see these 3 dimensions, but you could actually focus on, let's say, this particular XPU, its bandwidth is partitioned in these 3 dimensions, and that's statically done. The reason this is not great is once tenants carve out the slices they want to use for computation, there are some dimensions of bandwidth for every accelerator, specifically the dimensions of bandwidth that I'm showing you in red, that are idle, that are not utilized, because this is sort of the inter-allocation bandwidth. This is just statically partitioned, but we don't have a good way of using it without interfering with the traffic of a different tenant, right? And it turns out if you measure this at scale, what we find is from 33 to 66% of accelerator egress bandwidth can be left idle depending on how tenants carve out compute. Okay. Now, this is the problem. This is the challenge, and I'm going to tell you how we resolve this challenge using that technique of programmable photonic fabrics on the board of the server. Okay. It's a really simple idea. I'm saying let's replace this electrical connectivity with photonic links, the way that I was showing you at the beginning of the talk. Right? Now let's focus on this green XPU, this particular one that I've highlighted, and let's see what different capability this XPU now has. It still has those 3 dimensions of bandwidth, but what's beautiful about this new design is now you can program and redirect the egress bandwidth in the unused dimension towards a link that's actually going to be used by the tenant. Okay? And if you do that, if you can reconfigure the photonic fabric on the board of the server to redirect egress bandwidth in such a way, you're essentially eliminating having idle bandwidth regardless of how compute gets carved by tenants. Okay, so what this gives you is you program the fabric, you get contention-free inter-accelerator connections with theoretically optimal bandwidth, even when, in arbitrary multi-tenancy scenarios. That's the first idea, hopefully, that makes sense. And note that all the XPUs that were underutilizing their, vertical dimension bandwidth can all do this. They can do this within 3.7 microseconds or so. So at the time of allocating resources for new tenants, you can simply do this and eliminate idle bandwidth. All right. The second challenge that the design that I'm proposing helps you resolve is the challenge of accelerator failures. And this is sort of pervasive. We've been seeing a lot of work from both industry and academia that's talking about large scale, inference training jobs where an accelerator fails, and suddenly we don't have very good ways of dealing with that failure. So in this scenario, again, I'm showing you the state of the art where you have these 4 servers, each with 4 XPUs, and you've got one accelerator chip, that's the red one, that has failed, and you've got electrical links everywhere. The best thing you can do in this scenario is you halt the entire job, you find a free set of XPUs, you move the job there, restart it from where you were. Hopefully you have checkpointed and you've stored all the state that you needed to restart this job, right? So that's sort of one of the very popular approaches in industry and academia. Let's look
Rachee,
yeah.
We have questions from audience. I will quickly ask.
Yes, please go for it.
So does the design make the tiles at the farther end to only have 2 circuits possible at a time? If so, should the scheduling of jobs on the XPUs try to put the code-dependent jobs on XPUs in close proximity? Why not, 4 optical pathways to allow the full mesh?
That's a really good question. I think the diagram that I had was somewhat misleading, which made it seem like you can have, there's a limitation as to how many circuits you can simultaneously have, and that limitation is really small. That's not actually the case, because these waveguides that I was telling you about, they're, few nanometers in pitch. You can actually have a whole bunch of them, and you can have a whole bunch of circuits that utilize all the sort of, egress ports that you have from any ASIC, a GPU, a CPU, what have you. So that constraint is, I thought that initially maybe you were thinking about as the circuit gets longer, do you have low signal loss? That's certainly a concern. But at the scale of a single server board, probably not. You actually don't. We have done some measurements that, you can sustain that amount of loss. But the number of circuits that you can have, there isn't an upper bound on it. Of course, there's 10,000 waveguides you can have on the order of that number, but it's not very small, not small enough to be concerned about.
Okay.
Does that help?
We can probably follow up if there are further questions from the audience. Yes. Okay. There's a slight delay in the to get the response from the audience.
Got it.
So one more question is 3.7 microsecond is mostly the the 2 times of serialization and deserialization delays or something else? This is a significant delay. Any path to reduce?
It's a great question again. So yes, this is a significant delay. What this, as a system designer, what this reasonably makes, so this makes it hard for us to do this sort of change on demand while a job is already executing. Absolutely true. There's a lot of work that's happening in the photonics community that's trying to reduce this delay. There are certainly numerous papers that have been written about it, really cool and exciting work. This delay that I'm reporting is based off of a prototype that has been built, and I'm reasonably sure that that's a good bound to work off of. In research, people have actually shown much faster ways of reconfiguring these switches in silicon photonics. It's just that as a system designer, I'm making assumptions based off of technology that is, somewhat viable or fairly viable, if that helps.
Okay. Yep. We can probably follow up if there's more, follow-up questions.
Okay. All right. So I think I've got about, how much time do I have, Mingjin? My calculation is about 9 minutes.
Around 9 minutes, including Q&A, but you can probably try to leave.
I don't have that much left, so I'll try to not rush through this. Sure. Okay, so we were talking about the case of this XPU, the red one on the left side of the slide that has failed. Let's imagine now this brave new world that I'm talking about, where the connections between XPUs, so all of the black lines are now optical links, and you have this programmable capability on the board of the server. Now what you can do is you can find an XPU, specifically the blue one, somewhere in that same rack that is unutilized. It's lying free because you always have compute that's not fully allocated. And what you can do is you can take the neighbors of that failed chip and make photonic circuits between those neighbors and this new free available XPU in the same rack. So physically, this XPU is somewhat further away. It's not in the same tenant allocation, but because you can create these sort of direct circuits between a spare XPU, you can essentially get in-place fault tolerance. So you can pretend as if you're logically actually connected to now a healthy chip and resume the job. It's entirely, so that's something that can be done. Now, we actually built all of this stuff, and I'm going to show you end-to-end numbers, but let me first start off with the pieces that we built this testbed with. So we have a commercial silicon photonic mesh that we use in our testbed. This is essentially a 4-rack unit server that, when I first got it, I racked it in my bookshelf at home because, we didn't have space for it elsewhere. So that's how you rack some optics in a bookshelf. It essentially has this photonic mesh on the board of the server inside the box that you see, and there's a whole bunch of fibers that come out of that box, and that mesh looks a little bit different from the mesh that I was showing you before, but the underlying technology is quite similar. It's a programmable photonic mesh, and it exposes the ports at the edges of the mesh via fibers that you can then connect to GPUs, which is exactly what you do. Again, all the lines in this mesh are waveguides, and these colored rectangles that you see, these are the programmable switches that I was telling you about a few slides back. And there's, we can, in software, program the state of this mesh to construct circuits between any 2 ports. And we do that by connecting these ports to GPUs. And let me show you what that looks like. So this is, the right side is how you should actually rack your compute and your optics, where we've got 4 GPU servers that are talking to this photonic mesh using optical fibers. The logical diagram is in the center of this slide. So it's 4 GPUs talking to the mesh, and the mesh itself is programmable. And we also have a bunch of sort of a top of rack switch to connect to everybody. And we have a server that programs the state of the mesh. Okay, given this capability, we did what everyone wants to do. We evaluated how fast can we sort of fine-tune Llama 3.2, which is one of the more recent Llama models, And the thing that we are looking for is, given we have now enabled the hardware, the accelerators, to use more of their bandwidth, to essentially not leave bandwidth idle, regardless of how tenants are using the compute cluster. We've made more bandwidth available, and as a result, you would expect that the collective communication that happens between GPUs during inference is going to be faster, and that actually leads to a 70% speed up in the average time per epoch. So when we carve out different different allocation slices in this cluster, we're able to see that Morphlux, which is the system that we've built, gives you 70% faster or 70% better average time per epoch. Then the second experiment that we did with this testbed, among others that I want to bring to your notice, is that we, failed GPUs. So we said, all right, this GPU is now dead while it was inferring, on this model, on the Llama model. And you can see on the right bottom graph, on the x-axis is time, on the y-axis is tokens per second. So we are inferring on the model, and I'm just measuring the throughput in terms of tokens per second. We failed a GPU, okay? And using this programmability, the ability to program and in place replace the failed guy with a healthy chip, we saw how quickly can we recover from the failure. So when we did that, within a few seconds, we're able to recover from the failure and sustain the same throughput that we were able to before the failure occurred. And if you didn't have this capability, you'd have to do the more time-consuming thing of bringing down the entire job, migrating it elsewhere to an entirely different set of healthy chips, and booting it off of that. So in summary, I made a case for Morphlux, which is a programmable server-scale photonic fabric. It looks like the following. Instead of having electrical connections between accelerators on the same server, we are envisioning multi-accelerator servers where connections are actually optical. The top line results is say that you can get 66% better bandwidth in multi-tenant environments if you were to do this. So the egress bandwidth of the accelerator, you can use more of it. You don't leave it idle. The collective communication primitives can perform much faster, so 80% faster than state of the art, and you can in place replace failed accelerators within seconds during training or inference. And that is my last slide. I'll be very happy to take any questions you may have.
All right, thanks a lot for the great talk. Indeed, we have a few questions from the audience. So let me go first. Go with the first one. How do you recover from the real-world optical issues that can involve partial link degradation, laser drift, or the intermediate photonic switch elements failing, etc.?
So this is a great question. It's great in the sense that it kind of is more in touch with reality than I think this presentation was at a first glances. And I want to acknowledge that this technology, is actively under development, right? So people are developing the hardware components and deploying them at scale. Actually, deploying anything relatively novel at scale is a whole other ball game. It's a kind of effort that some of it happens in research, some of it actually has to happen at scale in industry. So there is work that talks about how do we deal with these challenges. It's more on the devices, the photonic side of things. The goal of what we are doing is looking at the hardware, seeing its capability, and building something end to end that tells us, should we iron out those issues of the heat and things staying stable and reliably working. If we iron those out, what do we actually gain from it? So those are challenges. All I can say is I acknowledge the hardware limitations of this relatively new technology. I don't have great answers for that. I'm just showing you a vision and a real world prototype.
Great, thank you. So one final question is there an electrical to optical conversion and vice versa between the serial and the deserializers?
Absolutely.
And the waveguide.
Absolutely, there is. So I let me try to actually yeah. So if you look at this particular slide, there's a serializer, deserializer. That's standard. That's there in, you can imagine it's there in all accelerators. That serializer, deserializer That at that point, you still have bits like any other chip ASIC would. And then the transmit receive block, that's the one that's responsible for doing the electrical to optical conversion. And once those bits have been converted to light, that's when that green line that you see, those are optical waveguides, then light is traversing on those optical waveguides. So absolutely, there's an OEO conversion that happens.
Okay, thank you. So we are at the at the right time. So let me just quickly introduce our next speaker. Our next speaker is Alexey Tumanov from the Georgia Tech. He will talk about the efficient LLM inference at scale.
Hi, am I audible?
Yes.
All right, nice. Sharing my screen.
Yep.
And the screen is visible, right?
Yes.
Okay, great. Good morning / afternoon, everyone. So my name is Alexey Tumanov. I'm an assistant professor at Georgia Institute of Technology. I am heading the Systems for Artificial Intelligence lab. And I've been blessed with a multi-year opportunity to collaborate with Cisco. We've published a lot of work together, and this kind of presentation, or rather where this presentation ends, is sort of the culmination of all of our activity that we've accomplished. So today I want to talk about efficient LLM inference at scale, and to set the foundation for this, we'll start talking about how to tame the throughput latency trade-offs in state-of-the-art LLM inference platforms, and how we were able to do that with Serve. Okay. So as many of you know, large language models have sort of taken over the world. There's an astronomical rise in popularity of large foundation models. They're pretty much everywhere, and they set the record for fastest growing user base. They're breaking all sorts of records held by human experts in terms of specific tasks. And so, very hard to ignore, both from machine learning and from systems perspective. And as Myunjin mentioned, this sort of become a matter of national attention, with federal funding actually being committed to develop the AI infrastructure, of course, with large language models actually occupying and spending most of that compute. As a matter of fact, Google's carbon emissions surge nearly 50% due to AI energy demand. And so with this meteoric rise and in the popularity of large language models, we also see a meteoric rise and the growth in the inference serving systems as well. Right, so we started very modestly. So here you have normalized latency on the y-axis and the request rate, or how many requests you can process per second on the x-axis. And so, of course, the early comers like FastFormer and Orca were to the upper left, but then very rapidly we sort of start seeing 20 to 30x higher throughput. And for any of the systems people in the audience, you will also notice that the normalized latency on the y-axis kind of hints at the problem that the state-of-the-art community is with the direction of the state-of-the-art community, and they were primarily focused on throughput, right? So my lab has been, and myself actually has been interested in latency-centric systems for more than a decade now. And sort of the question that we want to ask is there a way for us to actually come up with a balanced approach to simultaneously providing support for high throughput and latency? Can we maintain specifically low tail latency with high throughput at the same time? And so this is where I'm going to attempt to run a demo. So give me a second, I'll just open it in a separate tab. Okay. Oh, great, it works. So basically, what you're seeing happening here is that we're starting up a background server to serve requests with VLLM. You see that in the top right-hand corner. And what we're going to do, so basically it has started the server. You can see that it started the server and it's waiting for the application startup. And now we're going to ask the VLLM to give us a code snippet. So basically what you're seeing is the performance of the LLM without load, right? It's pretty smooth, no particular issues of note, and sort of it's generating things without any visible problems. However, what happens if we actually, in the bottom right-hand corner, if we actually start some additional load that joins the system? So we started submitting additional requests, and all of a sudden we see very visible stalls in the code generation on the left-hand side. And basically, these stalls are quite visible, especially from the perspective of interactive applications, where there's interaction between the user and sort of they degrade user experience. And it has to do, of course, with the tail latency that is being incurred by the processing of the requests on the left-hand side. And so these stalls kind of continue throughout the execution of this primary request that we're demoing here, which is the code generation request. They take up multiple seconds, in fact, so we're not talking about tens of milliseconds or even hundreds of milliseconds. These stalls can actually take up multiple seconds. Okay, so this served as a motivation for us. We go back to the slides. And what do we do about it? And how do we handle that? So in this talk, we're going to talk about analyzing the LLM batching policies. We're going to try to see if we can actually find a way of addressing this scheduling conundrum where you're simultaneously trying to get high throughput and low latency. We were able to find free lunch in arithmetic intensity as our mechanism, and we'll discuss how this led us to think about and implement stall-free batching. And finally, we'll sort of conclude with some evaluations and key results and analysis. So the question that makes sense to start with is what causes the latency throughput trade-off in the state-of-the-art LLM inference systems? And so I'm going to go through this very quickly because, after all, we are in the LLM inference or AI inference summit. So basically, on the left-hand side, you sort of have a prompt: is tomato a fruit, right? It represents our prefill, and it can be processed with a very large batch size, so lots of tokens can be processed in parallel. However, when you get to decode, you basically have to process or decode single token at a time for this given request, and sort of it's very sequential and iterative. So why does this matter? This matters because we get really good GPU utilization when we're processing prefill, and very terrible GPU utilization with very low parallelism opportunities or opportunities to extract parallelism on the right-hand side when we are in the autoregressive decode phase of processing this request, right? So that's really kind of the foundation to start with. Okay, so how do we improve parallelism during the code decode phase, right? Because it seems like we're doing pretty well with prefill, but decode is the problem. So can we find ways to actually improve the decode performance? Well, the first thing that should come to mind is, well, why don't we try batching, right? Batching across multiple requests so that we actually have multiple decode tokens to process at the same time. Okay, so in order to understand what happens when we try that, let's look at how batching actually works in the context of LLM inference. So let's say we have a timeline that goes horizontally left to right. We have two requests A and B entering the system. So this blue block right here corresponds to processing the prefill for A. Then you process prefill for B, and then you can start processing decodes for A and B. And so because you have two requests at the same time, you can batch the decodes across those two requests. So that's sort of a toy example that demonstrates where the batching capabilities are coming from, right? So now you have a batch decode. And then you can sort of continue to process batch decode until either A or B or both of them are completed. Okay, so that means that we can extract the decode efficiency because the efficiency increases linearly with batch size. So increased batch size gives us increased throughput. Just to finish that off, right? But here's the problem. So let's say we're in the process of processing decodes for requests A and B that are still in the system, and two new requests enter the system, C and D, right? So we have a couple of options of how to handle this. Here's option number one. Let's go ahead and start processing the prefill component of the C request, right? And the prefill component of the D request. And then we have an opportunity, an even greater opportunity to actually batch even more decodes together. So it is a very well-known fact that we can actually increase the opportunities for batching by simply waiting a little bit to batch. And so our batch size increases, the performance of the batch decode increases as well. But the problem is that you can see that the decodes are now stuck behind all of the prefill processing that you had to wait for. And that's exactly the kinds of stalls that you're seeing in the demo previously. So decodes for the request are stalled. You get very bad tail latency, and it's also a function of whatever requests you're currently accepting into the system. Well, seems like a problem, right? Can we take a different approach? Let's try to prioritize decodes instead. And so it's also informed by enough systems theory out there, specifically shortest job first policy and things like that is known to sort of minimize latency for the scheduled jobs. And so will that work? Well, it does minimize latency for the decodes, right? So in this particular case, you are prioritizing decodes that are still in the system, and only after you finish off all of the decodes, and then you start processing prefills. But the problem with that is that because you now have very, very, very limited opportunity to batch your decodes, your throughput is going to suffer. So this is a sort of quintessential example of this fundamental trade-off that we always experience in systems between throughput and latency on this one slide, right? So that's why it's sort of hard to achieve both. So at the bottom, what happens is that we don't have enough opportunity to batch decodes, and so this leads to low batch size, which leads to poor throughput. And by the way, at the time this work was published at OSDI 2024, basically VLLM was doing whatever we described at the top, and the faster transformer was prioritizing decode at the bottom. So this is the trade-off that the state-of-the-art systems at the time have sort of created. So on the y-axis, you have throughput. On the x-axis, you have decode latency. And we start with faster transformers. Then iteration-level batching was introduced that led to Orca, which was prioritizing prefill. And then paged attention was introduced, which led us to VLLM. And you can sort of see this progression from bottom left to top right, right? In this trade-off space, meaning that we are chasing throughput, but we're paying latency in order to chase that throughput. So the state of the art at the time was sort of in the bottom right-hand corner, in the top right-hand corner, I should say, but where we want to be is in the top left-hand corner. Highest possible throughput, lowest possible decode latency, right? So existing batching policies, they make harsh latency throughput trade-offs. As you can see, where we want to be is in the top left quadrant, where we get maximum throughput with decode latency, and that's where Rachee sort of ended up. Okay, so how do we achieve both at the same time? That's the key question, right? Well, let's consider a third option here. If we can neither prioritize prefill nor prioritize decode, we have to figure out a way to do something in between. And that something is perhaps batching prefill with decode, right? In other words, introducing mixed batching into the picture. So mixed batching, the idea here is to actually fuse the computation of the prefill tokens that's performed on the prefill tokens and the computation that's performed on the decode tokens into the same batch. Well, sounds like a great idea, so let's give it a shot. What we end up with is actually what you see on the top right-hand side. Y-axis is the batch time, basically how much time you spend processing a single batch. And on the x-axis, you have increasing batch size, right? So what you, in the orange, you have the batch time for decode only. In the blue, you have the combination of decode and full prefill. In other words, what happens is that we pay significant cost for processing full prefill with decode mixed in the same batch. So that's the challenge. If you try to attempt to do this naively, by combining prefill and decode operations, this leads to a significant increase in latency that you don't necessarily want to pay, right? Because remember, we still want low latency. Okay, so here's another example. Let's say you have decode latency of 10 milliseconds, and with VLLM, let's say we process the decode for request A, and let's say it can happen in 8 milliseconds, right? But then the prefill comes in, we process prefill because it's prefill prioritizing, right? And then we process the decodes for requests A and B in a batch. So here, as I mentioned previously, we're paying the head of line blocking, we're paying the stall latency, and we end up with very bad latency that misses the SLO deadline. Orca attempted mixed batching with a full prefill, and this also runs the risk of violating the SLO deadline because, as you can see, you do have to pay the cost of the full prefill latency when you're mixing them together with decode. So the key insight here is that we can't really batch with full prefill. Well, if we can't batch with full prefill, we really have to chunk it up into slices, right? So in other words, prefill computation can be done at a marginal cost with very careful batching. And so let's go through this slide to understand the insight that we're really leveraging here with arithmetic intensity. On the y-axis, you have arithmetic intensity, which is basically how much compute you're performing per the single fetched byte of memory. And on the x-axis, you have the number of tokens. Okay. And at the top, you basically have the compute bound region where the amount of compute that you're performing per fetched byte dominates. Whereas at the bottom, you have the memory bound region where the amount of time, the end-to-end time that you're spending in compute, the end-to-end time that you're spending on a batch is spent more on memory fetching than on compute, right? And so at the bottom, the latency is dominated by the wait fetching time from HBM memory to the GPU cores. At the very top, and that's largely independent of the number of tokens in a batch. At the very top, you have latency that's dominated by compute, and that grows nicely linearly with the number of tokens. So the top part of this is basically where we would like to be. This is where prefill is, and that's why we saw the thumbs up previously, because prefill is very arithmetically intensive operation, but decode is not. It's very memory intensive operation, right? So it's constrained due to memory overhead and decode phase. So where we want to be is in this point of intersection that we're referring to as sort of the balanced arithmetic intensity, where the amount of time you spend on compute is the same as the amount of time that you spent on memory overlap. That's what Rachee Singh is trying to achieve. So this led us to the idea of stall-free batching. The key idea here is that we split the large prefills into smaller chunks. So in other words, we are taking this finer granularity approach, and we're splitting them just enough to consume the leftover compute budget in every single decode batch, right? So remember, we simultaneously want to chase latency and throughput at the same time. And so to chase the latency, we have to be making decisions in an SLO-aware fashion, not just sort of get latency improvements by chance. So these latency decisions are taking advantage of the knowledge of the TBT SLO, the time between token SLO. And so that's our latency slack to work with. We figure out how long the decode batch is expected to take, and whatever the leftover budget is going to be spent on the large enough chunk of prefill in order to piggyback on this decode computation. So with the baseline VLLM, basically remember that you have, let's say, 8 milliseconds to process a decode batch, and as you're processing the request, one way to conceptualize this is that you're constantly oscillating in the arithmetic intensity space, right? So you're always going from very high arithmetic intensity to very low arithmetic intensity, and this oscillation kind of gives us intuition that some performance is left on the table. So in this particular case, you're paying the latency cost for the decode batch. What we are trying to do with Rachee Singh is we're essentially breaking this vicious cycle by partitioning the prefills into chunks and batching the chunked the chunks of prefill with the decode tokens, and this sort of evens out the oscillation in the arithmetic intensity space and gives us the compute memory balanced approach to processing these mixed batches. So now, because we're also doing it in TBT SLO aware fashion, we're able to achieve kind of very high latency SLO attainment. And in addition to this, we also get the gain, so this improves the throughput as well. Okay, and so this brings me to a second demo that I'm going to open right now. Should show up on the screen momentarily. Okay, and what we're doing here is we're going to run VLLM and Serati Serve side by side. I should mention that the workload is exactly the same what you saw in the previous demo, and we're still instructing both of them to sort of generate the code snippet. And you can see that these stalls are happening on the left-hand side, as we previously discussed, while on the right-hand side, the generation is very smooth. And it's sort of not smooth by accident, it's smooth by design, because we've been batching these mixed batches in an SLO-aware fashion. So there are no stalls on the right-hand side. Okay, I can play this again. There are no stalls on the right-hand side whatsoever. And as a matter of fact, the Serati Serve component actually completes faster because it is able to achieve higher throughput as well as higher latency SLO attainment. Okay. Now back to the slides. All right, in terms of evaluation, basically, just very quickly, because people call them different things. So we are talking about TTFT, which is time to first token. It's the time required for the first token to show up from the time user submits a request. And the TBT is time between tokens, is the latency between each output token. And this additional metric that we introduced is what we call capacity, or max capacity, is the maximum QPS that you're able to achieve with a given system, with a given workload and a system pair, right? And maximum QPS that can be served while satisfying latency SLOs, imposed both on TTFT and TBT. So this is a good sort of combined metric that tries to capture, how well are we serving both of the SLOs at the same time. The setup was using shared GPT-4 trace on A100 GPUs, and we did try to run it with both strict SLOs. And for those of you who might think, oh, this only works when your latency SLOs are strict, we also tried this with relaxed SLOs as well, where you do have more time to actually process bigger prefill chunks. So let's see. Yeah.
So Alexey, we have a question from the audience.
Okay.
Let me just read it. Do you see the architectures like a non-auto-regressive transformers, retriever augmented models, making these scheduling optimization obsolete?
Non-autoregressive, well, this only applies to autoregressive transformers.
Okay.
Right.
Yep.
Yep. This whole talk is about autoregressive transformers. So actually, it's still a good question, because chunking prefills can help you in other ways. So it's not going to help you because you don't have to concern yourself with mixed batching, so you don't have any decode tokens to worry about, right? But it can help you to achieve this finer granularity that sort of underpins, as one of the insights, this work, as well as some additional work that we published on multi-million token long context LLM inference support. So in that latter work, if you have the capability to chunk your prefills, you have the ability to preempt long context requests in order to slip in the short context requests. So even if you're not generating decode tokens, you can still take advantage of chunking in order to achieve this finer granularity for scheduling across the heterogeneous set of requests on the same platform.
Oh, yeah. I think that makes sense.
Yeah.
Okay, so just to time check, including the Q&A, you have the 6 minutes or less left.
Absolutely. Yeah, I'm actually almost done.
Great.
Okay, so basically this is the result that we achieved. The results were sort of evaluated on two models, Llama 270B and Falcon 180B. And notice that we did try it with a strict SLO as well as relaxed SLO pairs. And the comparison was drawn against Orca and VLLM. And we can sort of demonstrate that we are able to achieve 5 to 6x higher capacity, as previously defined, right? The ability of generate 5 to 6x higher QPS subject to maintaining TBT and TTFT latency SLO attainment. So in summary, the problem that we tackled with this work is that state-of-the-art systems sort of had to sacrifice decode latency, especially tail latency, in order to achieve higher throughput. In some sense, they were sort of hoping to achieve good latency performance by virtue of making throughput faster. So the key insight here is that the low arithmetic intensity of decodes does actually allow us for slipping in, for piggybacking with this compute-intensive prefills with negligible decode latency cost. And the results show that we can achieve optimality in both latency and throughput, leading to 6x higher capacity under the SLO constraints. So we're satisfying SLOs and we are kind of gaining on throughput as well at the same time. You were also able to see that with the demo, where the latency benefit could be seen by the smoothness of the generation on the right-hand side of the demo, and the throughput could be seen visually by the fact that our task ended much sooner than on the left-hand side, right? We do enjoy quite a bit of industry adoption at this point in time. As a matter of fact, the Rachee Serve scheduler was already implemented in VLLM as a default scheduler. It was also adopted by several startups, including Sentinel and Anyscale. These are the QR codes for the paper, GitHub, and its use in VLLM. And of course, the natural next step is for us to sort of try to get Cisco excited about this and use it in production in our continued collaboration with this amazing company. And that's it. Thank you.
I don't think we actually have the question from the audience. So let me actually ask the one question. So what is the kind of upper limit you can think of the throughput or the latency bound when the chunk prefill is applied? Is there any theoretical the work that has been done?
So upper limit on the throughput or latency as a function of
maybe.
So first of all,
yeah.
Basically, it's very hard to analyze analytically, and so actually for that reason we have started a separate project where we implemented a discrete event simulator that tries to give us the performance predictions, a high fidelity performance prediction end to end as a function of different config parameters like the 3D parallelism, the scheduler that you're using, the GPU SKUs, and the workload and the model, of course. And so this is the project that we've actually been working on in collaboration with Cisco over the course of the fall semester. Theoretical limits are really, really hard. What we can, and the people have tried that, but they usually have low fidelity. And so the fidelity with the theoretical models doesn't give us very good results. Fidelity-wise, the theoretical models don't really give us good results. And so we were able to achieve much better results with sort of an empirical approach of implementing a simulator instead.
Okay. One small, follow-up question. I mean, one small additional question is, what about the GPU utilization? You said, you're actually balancing between the latency and throughput while, leveraging the extra computation resources available, right? So did you actually measure the GPU utilization?
Yeah, this I'm not going to attempt to go back to that slide, but basically, if you hit the perfect middle ground between memory intensity and GPU intensity, the way to think about this is as follows. So you have a bag of ops that you need to perform, and in that bag of ops, there's going to be sometimes spent on compute and sometimes spent on memory fetch, right? And with the assumption of full overlap, let's say we were able to somehow achieve full compute and memory fetch overlap. What you want to keep those two times balanced, because if one dominates over the other, you're leaving some performance on the table. And so basically, because we're doing this by design with the Rachee Surf mixed batching approach, we are able to achieve the highest possible GPU utilization. So it never waits, and it's always busy computing something. Yeah, and so basically that's sort of the holy grail, is to be able to achieve this sweet spot in this arithmetic intensity the trade-off space where you're spending roughly equal amount of time computing and fetching memory.
All right. Yeah, I think that answers my question. Thank you. Thank our speaker again, and then our next speaker and the last speaker is Neeraja Yadwadkar. So she will talk about the intent-based serving system for LLMs today.
Thank you, Minjin. Let me quickly share my screen.
Sure.
You're able to view my screen now, right?
Yes.
Okay. Thank you once again, Minjin, for that introduction. My name is Neeraja Yadwadkar. I am an assistant professor currently at UT Austin. First of all, I would really like to thank Cisco and especially Minjin for arranging this or organizing this highly timely, I would say, summit. And it focuses so much on particularly AI infrastructure, but AI infrastructure in inference serving, which makes me very excited. So I decided to talk about our, this is kind of ongoing work in my group, but I'm excited about this. And I'm going to talk about how do we build serving systems for LLMs that also are accessible to, a wide range of audience, from expert audience, expert in machine learning to expert in other domains, to novice users who just want to use and benefit from all that LLMs have to bring to table. All right, so this is obviously a work that cannot be done with students, and I've listed a few, but the whole group, my group is called UT SysML at UT, is actually heavily invested in all these projects that we are doing on LLM inference. All right, so let me begin a little bit by saying, as I said, I am at UT currently. I got my PhD from UC Berkeley, and I was a postdoctoral research fellow at Stanford, both in the CS departments. And research-wise, just to set some context, I basically am a cloud computing systems researcher, and I have a strong background in machine learning, and I use that for building systems that benefit, first of all, from the agility and stochasticity that machine learning models bring in. And also now, one of the things that I'm going to talk about, actually the talk is focused on an inference serving system. How do we understand what the requirements are of machine learning models? What are the requirements from applications? And how do we tie that nicely into building a system? So that's what I'll do in today's talk. I think, you've heard 3 talks so far, and every talk has, and even including Minjin's talk. So in 4 talks, you've heard that, yes, LLM-based applications are they are emerging, right? They're only growing. And so I don't think I'm going to spend too long motivating that. I'm just going to directly try to motivate the point that every application ends up creating workloads that are very different. Okay. So obviously, for generating these images, for instance, I used an NLP, DALL-E. I asked it to produce a chatbot or virtual assistant kind of an image for me, and this is what it got me. Then I asked, give me, content creation kind of a use case, give me another picture. So this is, first of all, multiple modality and all of that. But what I want to focus on today is when we talk about LLMs used in such different contexts, Depending on what we are asking behind to a model that is used behind the scenes, can actually end up creating different computational loads. For instance, for chatbot, take an example of Alexa, Google Assistant, or even ChatGPT. These are kind of supposed to be interactive environments. They are supposed to give me answers as you do in a one-on-one conversation, in a one-on-one conversation with someone. So the context is very important. You cannot forget context and act stateless in such conversations. So context across queries is important, and you have to keep the text generation to light, because you're not going into a monologue, it's a dialogue by definition. In content creation, on the other hand, for example, can be used for drafting articles, drafting emails, or even today in my class, I'm hearing from students that they're using ChatGPT for summarizing a paper, for instance, right? So LLM behind the same interface can actually be tasked to do various different things. For content creation kind of applications, you imagine it not being as real time or latency sensitive as the let's say Google Assistant or Alexa. But this is rather a best effort or batch oriented kind of workload that is observed. And to achieve that, we require long context management on part of the LLM behind the scene, and we require it to have creativity and generate longer texts. Right? Now, you would say that true, but how many such applications there are? And actually, if you remember the very first slide of Mingjin, the list kept going on. But even if we just focus on one such workloads, let's say I only talk about chatbots or virtual assistants. Even in that case, if we use these chatbots in different contexts, so I took an example of education versus healthcare. Depending on what you ask them out of them, what you care about changes. You care about accuracy in education also for understanding a concept, let's say, when you're talking to a chatbot. But in healthcare, I'm asking it to predict what patient treatment should be, and their life is at risk. So accuracy matters the most. Privacy obviously also matters in healthcare more so than in education. And inference latency and cost actually depends on, even in one domain, it depends on what is the context there, right? Are we asking these questions during an operation, a procedure, or are we asking these questions, just to get feedback, reinforcement, or expand what medication brands are existing there. So even if we focused on one particular application, the workload that it ends up generating and the things that it expects from these LLMs can actually be different, right? And the good thing is these LLMs, if you looked at like any paper today, not just in conferences, machine learning conferences, but also on arXiv today, you see every day new papers coming out that are talking about, okay, if you deployed my LLM in certain way, if you applied this particular optimization, this is how the characteristics change. A few things that I've noted here, you can thinking about models that either do not fit on a single GPU, even models that fit on single GPU can benefit from parallelism. And there are various ways of parallelizing, and some of those were talked. I'm not going to talk about and give you a primer on how these parallelism or compression techniques work. But in parallelism, you can think about tensor parallelism, where a layer itself kind of gets distributed. In pipeline parallelism, you're distributing the model one layer at a time, executing one or multiple layers on one GPU, and that's how you distribute it. In MOEs, which was also one of the topics that was brought up, expert parallelism is very well known and used. That's just natural way of distributing MOE-based models. And there are combinations. These are not, kind of mutually exclusive techniques. You can apply them in combination together, thereby increasing the number of ways you could have deployed it and achieved different characteristics in terms of, the inference latency or throughput, or sometimes even accuracy. Less so for parallelism, but the accuracy matters more when we're talking about compression techniques. Where compression techniques basically focus on how do I get my model to fit in limited amount of resources. Quantization and pruning are well known, but there are knowledge distillation and other such techniques that exist too. Pardon me, I'm on a older computer, so I do not know. There might be unknowns that might be thrown. This laptop goes back to Berkeley. I'll be dating myself, but just saying that there might be such pop-ups that you might see. Pardon me for that. All right, so in compression, two of the major techniques that I wanted to just note here are quantization and pruning. In quantization, you can have full precision, let's say that is floating point 16, or you can go on reducing precision of computation at the cost of accuracy sometimes for latency. There are ways to actually maintain accuracy even with quantization, where you just save on memory by storing quantized weights and KV cache and activations. But when you're computing, you convert it back to full precision. So thereby, there is way to preserve accuracy while still gaining on memory capacity and latency. Pruning, structured, unstructured, and a lot of such techniques exist that actually are very model specific. So let me give you, a better visual of what that ends up meaning. So we played with a Llama model. I believe it was Llama 27V model, and I'm just showing a few options. Let's say I did not do any quantization. I went with FP16, full precision. With this model, then I can apply different degrees of parallelism. PP2 means let me have a degree of 2 for pipeline parallelism, divide that model layer wise, and then sort of go for tensor parallelism on top of that. And we measured various characteristics, inference latency, and how big the model was. Because when you apply such techniques, you end up incurring overheads. When you're saving on one metric, the other metric changes. Similarly, you can change, and I think the cluster that we used had, or the server we used had 8 GPUs. That sort of limits how many, what degree of parallelism you could use, right? So we did this for a bunch of options. You can start with quantized model and then apply parallelism. You can start with a prune model and so on and so forth. And if you notice the sort of small boxes below, the latency that you observe, the memory that you actually need for that particular configuration of deployment for that model can change. And I only have like these few options that I could show on this slide, but even for this one model for our small cluster, we were able to have 145 different options that actually had their latencies and the metrics that you care about all over the place. This space is large. And so just to quickly capture that, we played around with a couple of versions of Falcon, GPT-J, and Llama 2, 3 versions of that. And if you look at that particular line that I'm highlighting here, the configuration space is really large. And it's not just large, but it also ends up creating differences in the metrics, as like I said, that you would care about. So then obviously the question now is when there are so many of these applications that are requiring different things from these LLMs, how do developers choose? Right? So obviously, very important problem, and so it's been widely studied. Right? So there is a lot of work, and I'm going to talk about 3 kind of picks from representative categories, beginning with accelerate, or what exists, from industry, for instance, that allows us to serve inference in a managed fashion. So that's that. From academia, we have multiple works, including Alpasav, Vidur is from Alexey, who's just gave a talk right before me. So all these systems have basically looked at this problem from different angles. Not exactly this problem, but how do we basically improve inference serving, right? Accelerate is a library that allows all these knobs, or chooses default options when users do not have those knobs figured out for themselves. But combined, let me say that there are certain limitations that induce inefficiencies that motivates our work. First of all, libraries like Accelerate, or even Bedrock from AWS, like all these industry level inference serving systems, they provide these knobs where users can go ahead and tune those. Knobs meaning what should be the degree of parallelism for a certain type of parallelism, if I should quantize the model, what kind of quantization technique should I apply, and so on and so forth. Which is good if you have the expertise, right? Or if you do not want to have to make these choices, which actually impact what you gain from inference requests that get served, they choose default options across LLMs. And again, that is a problem because it ends up being suboptimal in our observation. Some of these systems require code changes. They require users or developers to bring their models in a certain format that then can be automatically placed hooks into to measure stuff and automate certain things. Again, requires expertise from users that we believe in this work is not available with everyone. And so it limits access of all these excellent advances that we are seeing from machine learning community. The other limitation that I do want to bring out that motivated my initial pitch for this work was a lot of these systems end up assuming the knowledge of the workload, meaning they assume what models are going to be deployed, what inference requests are going to be served using those models at what point in time, which is unrealistic to know from user's perspective. Just looking at how we use all different models around us. There can be certain predictability, but that limits, once again, what could be usefulness of these models. And then most of these systems rely on simulations that are not real environments, focus on just one model that needs to be deployed. And if none of these are the limitations you want to go for, the only option you're left with is profiling your actual big LLMs, which ends up being prohibitively expensive because you would have to deploy every LLM on your expensive GPUs for all these different configurations. So I don't have to paint the picture of how that sort of ends up impacting environment, and nobody would actually do that, right? So that helps us set our goal. In this work, we basically want to meet the intent of the user rather than asking them to specify exactly how to and what these knobs should be set to. We ask them, what do you care about? And then we want to provide this while keeping in mind the ease of use. Because a lot of my work actually comes from this philosophy that ease of use traditionally is assumed to come at the cost of performance, because the more you abstract, the more control, the knobs that you take away from users, it comes at the cost of performance, meaning you cannot use your expert knowledge to tune a system to get the best performance. HPC folks would actually agree to that. But in most of my work, the theme has been that we design systems for ease of use. We come up with interfaces, abstractions for ease of use in a way, and then build the system to support that abstraction, support that interface. That ends up allowing us actually the opportunity to improve resource efficiency behind the scenes, rather than taking orders or specifications from users. So to achieve this goal, particularly in this context of LLM inference serving system that we are building, we wanted to assume no knowledge of future inference requests, which we, as I said, believe is not available. We want to handle dynamically changing multi-tenant serving environment, where you can introduce your model at any point in time, and we will start serving requests for you using that model without you having to go to any simulation environment and then figure out how to actually deploy. So what we have built is iServe. I stands for intent-based serving system. That is a full-fledged inference serving system that allows for all these different use cases, so as to say, where you do not need to know your future requests. You can work with sharing the environment in a multi-tenant LLM serving fashion, and yet achieve low costs, because the whole point was building cost efficiency that comes through resource efficiency behind the scenes from the system's perspective. To help us achieve this goal, we introduced two key ideas in this work. The first one is fingerprints-based profiling, which would allow us to get accuracy without incurring the cost of profiling. This is very crucial. And then secondly, because we want to survive in the multi-tenant serving environments without assuming the future, the knowledge of future workload, we focus more on how do we actually deploy after we know what to expect in terms of resource requirements and latency and performance kind of estimations. How do we go about loading the model on the GPUs in a cluster that are available? Placement problem. So let's begin with the fingerprint idea. I don't have too long, so I'm going to try to capture the sense of this work. Actually, so let's, without going into too much detail, primer on LLM. This is kind of a full LLM architecture of a typical decoder-only LLM looks like. So you start with inputs, you go through a bunch of layers, you compute embeddings, and then you compute your attentions and a bunch of repeated layers that sort of are common in these deeply learned models until you reach softmax, and that gives you your output. One thing we noticed was that most of these typical architectured LLMs have repeated hidden layers, right? And we basically looked at a essence. How do we distill the essence of this full LLM architecture without worrying about repetitions that exist there? We basically then decided that let us dedupe, in some sense, this full LLM architecture and come up with a fingerprint that captures only the unique layers. And we made an observation using such reconstructed model that we call a fingerprint of a model, that as the number of layers change, so do the number of seconds or the performance and amount of resources used, memory used, changes for the whole LLM. So there is a direct correlation that can be exploited, which basically gives us an idea that instead of having to profile using the entire LLM, which needs to be loaded and then requests need to be served just to get an idea of what configuration to use, we can actually use this essence, the fingerprint of these models, to reduce that, to achieve the same goal, right? So to understand that, this is kind of the crux of the story. How do we go about using this fingerprint, measuring using just the fingerprint, profiling using just the fingerprint, and estimate for the entire LLM? We estimate the inference latency and memory, which are the two knobs we have focused on in this work. So let me start with inference latency. To understand that, we have to understand, this is a little bit of primer now, but I'll quickly get to the point. How do we break down? Where does the inference latency come from? And the previous speakers have talked about this. When you load a model, particularly this kind of a model, your query, basically a bunch of tokens that you have provided as a query, go through the prefill stage. And this is when you incur most of the time, which is called time for first token, TTFT. And then after that, one token is taken as input and one token is produced as output until the end of the query, right? And so the total latency of this inference query ends up being TTFT, the time it took initially to process all the input tokens, and then the number of output tokens were produced times the time it took for that, right? So now I'm actually going to show you the use of very simple high school math, if you will, that helps us use the fingerprint in a way we can profile and get certain variables answered to get to the latency of the full LLM. Okay, so hang on with me. What we notice is, if we know TTFT and TPOT, we know the latency of the full LLM, right? So now, how do we do that? First method that you can think of is, it's two equations. It's two unknowns, two variables. We need a system of two equations to solve. We'll get that answer. It's a very, very simple high school level math, right? So if you load a model and send two requests from it, you capture the latency, you measure the latency, you write these two equations, and you solve for TTFT and TPOT. You got that, right? You will get those answers and you would be done. But the problem is, you would have to do this for every configuration. It's nice that it's only 2 profiling runs per configuration to get to this, but it is very expensive. Instead, what we propose is, let's use this fingerprint. Let's send a request. So from the fingerprint instead of the whole model. In this fingerprint, we divide the layers into, the unique layers, the other layers, and the hidden layer that we know repeats. Okay. So now when I have a request that is going through this fingerprint, I further divide the TTFT for that fingerprint into these 2 blocks, the other layers that it has to work on and the hidden layer that it has to do. Similarly for TPOT, that gives me, instead of one variable, it gives me 2 variables. From TTFT fingerprint, I got TTFT other and TTFT layer. So now instead of 2 unknowns, I have 4 unknowns, right? So this is going to take, like if you just extrapolate it from what I was talking about, simple high school math, is going to require me a system of 4 equations with 4 unknowns. Once I have that, I can go from these values, TTFT other and TTFT layer, to the values of TTFT and TPOT for the whole model, which will give me the latency for the whole LLM, right? So we can do that by having 2 fingerprints, because you still do not know how much a layer, how long does a layer take. So this is like a little bit internal detail. We have 2 fingerprints, fingerprint 1 and 2, one with 1 hidden layer, one with 2 hidden layers. And we send 2 requests, we come up with a system of 4 equations, and we solve each of those for the fingerprint level variables and then put them together to finally get the value for the full LLM using this. In the interest of time, I'm rushing, but my understanding is I only have, 6-7 more minutes. I'm not able to...
6 minutes, including
Yes,
the
right.
Q&A.
Okay. Feel free to ask questions in any time. My next such small section is going to be about how do I go about using fingerprints to estimate memory. It uses the same principles, like again, very, very simple high school math. But here you need to understand what memory constitutes of. If you don't have parallelism, you only have the weights and activations. So your footprint of memory is just the weight, the memory taken for the weights and the memory taken for activations. For tensor parallelism, you gain latency, but you carry overheads in terms of memory, because you have to carry, you divide the weights across the GPUs, but you carry activations. And that's what the memory footprint ends up looking like on the last column. Not going to go through the details, but like I said, you can also have tensor and pipeline parallelisms together, and that's what the memory footprint ends up looking like. So if you focus on the last column, again, we notice there are 3 unknowns here, right? And we apply the same logic without going into the details. I have the slides, and you could take a look at that later. I believe the slides are self-explanatory. But again, you would imagine that I need to solve for these 3 unknowns. So I'm going to somehow use my fingerprint to measure enough that gets me these 3 equations in some sense, right? And I solve for that. So I get values for this. The good thing about memory footprint is that you do not need to worry about solving these for each configuration. Once you get values of these 3, you can simply plug in what the degree of parallelism you have and get answers to that. You only have to worry about compression techniques. So for each compression technique, you need to do this once. Okay, so as I said, in the interest of time, I'm not going to show this, but all this really simple math explained in a elaborate fashion, you can find on the slides. Okay? And we obviously utilize that, the observation that you can go, actually, there is a direct correlation between number of hidden layers to the memory that they require. We apply that principle. Overall, this fingerprint-based profiling mechanism was able to, fetch us the most gains in terms of profiling costs compared to existing systems. And obviously, there was the trade-off was, it's profiling using a smaller representation of the model, but we were able to keep the estimation errors below 7% on average, which was fine actually, because the 7% in terms of these large models in terms of memory is not much, and you anyway need to have some buffer for dynamically generated. Okay, so bringing you to now the system, because this was like the main thing that was required to make a headway in how do I even go about thinking about deploying this, right? So this is what the system looks like, okay, as a whole. But let me tell you, layer by layer. We interface with 3 personas. There is a model developer that comes up with a model. App developer, this is a persona that has the user intent for which the application is being developed. And finally, the user, who basically has inputs and asks the query. I serve as a system has 2 components, a controller and actual worker machines that execute a query on user's behalf. So all these 3 personas interact with the controller that has 3 components. The fingerprint controller that we just talked about generates a fingerprint, profiles it, and estimates different configurations, memory, and performance that to be expected. The app developer interacts with the deployment controller through user intents. Deployment controller uses this kind of estimation in terms of configuration map from fingerprint controller to come up with a deployment plan and deploys the LLM to meet user intents, taking into account the availability of GPUs, which is where the dynamic component comes in. Okay, so let's focus on the deployment controller for another 30 seconds. The deployment controller selects a configuration that meets user intent, selects LLM to GPU mapping, and deploys a model. The first 2 are actually intertwined. But still, let's say we select a configuration that, that's a table lookup from the configuration map that meets user's intent. But how do we select what GPUs to use for actually deploying once we know how many GPUs and what kind of configuration in terms of parallelism degree and so on and so forth is required. So we played with, for understanding that, we realized that you have to take into account load because you do not know what the situation is in a multi-tenant environment and what the workload to expect is. So we played around with 3 strategies that you could imagine. Least loaded, where you sort of find GPUs that are least loaded and you go behind them. You pack well so that you save on resources, save on GPUs, or a hybrid strategy that, depending on load, either packs at low load situations or distributes on high load situations. We ended up going for hybrid given load for the results that I'm going to show. But iServe as a system is modular enough that you can replace any of these strategies with new. So I just want to say that this framework that we're building enables further research there. Lastly, for
we have one quick question
Yeah.
from the audience. Does this study consider same GPUs? How does the fingerprinting work when there are GPUs from different families?
Right. So for now, that's a great question. But right now, we in our cluster, whichever GPUs are available, we are using that same cluster. We are sort of harvesting the GPUs that are not being used for inference serving for this. And yes, we haven't solved the problem of how do we go from, we know the capacity of this GPU for handling these inference requests in certain given time and cost. How do we go from there to extrapolate about other GPUs? What we realized was it's highly dependent on what you use. And so the problem is even more interesting in that context if we have heterogeneity in the cluster. But so far we have assumed homogeneous. Okay.
I'm totally
can you
wrap up the 1 to 2 minutes within the 1 to 2 minutes?
Sure. I'm not going to talk much. Anyway, the scheduler is, again, please remember that there are modularities in the design system. And so every component that I'm talking about is the first step towards making this feasible, and we can innovate further. I don't have the time, but I want to promise you that we are able to minimize latency. So user intent can be just to minimize latency, minimize cost, improve throughput, or meet a certain latency, meet a certain cost budget that they may have. And so the evaluation, we compare against Accelerate, AlpaServe, and TensorRT LLM, which is what we built our system on, which is a newer version of faster transformers for so we show that at different load situations, we are able to minimize latency if that's what the intent user chose, but we are able to do that compared to other systems while maintaining throughput and reducing the GPUs, particularly taking advantage of the load-aware GPU model to GPU mapping. We also are able to work with different intents, being intent-based inference serving. We are able to optimize for cost, memory, GPU hours, if that's what the users end up choosing. We also meet specific targets for different intents. So meeting certain latency SLO, for instance, we are able to show that we achieve, we maximize the SLO attainment, again, compared to these state-of-the-art systems. And we can do that for relaxed or most tight SLOs too. With that, I would stop here. iServe is an intent-based LLM serving system. And through its fingerprint-based profiling mechanism, it is able to reduce profiling costs, meet user intents, and do that while achieving resource efficiency. This is an ongoing project, and we have follow-up projects that are planned on top of that. So if you have thoughts, comments, questions, please feel free to reach us. Thank you.
Thank you, Neeraja. So I think in the interest of time, we can directly switch our gears towards the panel discussion. It'll be great. Oh, by the way, let's thank our speakers I really appreciate your great talk and participation. So let me monitor if there are the questions from the audience first for your individual talks. In such a case, we can actually have some discussion around the audience questions. Otherwise, I can actually kick off with some questions I prepared. The first thing I want to actually discuss is personalizing inference. Because nowadays, embodied AI and RAG or the agentic framework, all those things, probably to aid the user-specific problems and tasks, right? So I'm guessing that one question I would like to ask is RAG, the retrieval augmented generation, still relevant to invent a reasonable solution for the personalized the inference solution? If so, what would be the system level challenges, or what alternative approaches do we have to consider as a researcher? Does anyone wants to give it a shot?
I could, because I'm unmuted right now. I could give it a shot. Or Rachee maybe. I don't know.
Neeraja was like, she has a bunch to say. I mean, I can say a little bit about maybe the systems challenges, and again, this isn't, please feel free to jump in. I think, across the board, all the talks that we've had, folks have thought about having limited memory and essentially doing as much as we can with the limited memory. I think in that vein, RAG does present the same challenge, which is, you can only have so many adapters. How do you load them fast enough? Which ones do you keep? Which ones do you not keep? And there's already existing work around that. But I think the memory component is one core systems challenge that I see. I don't know, what do other folks think?
So I think just overall, I think it's a mixed bag, Minjin. It seems like RAG can be useful for sort of personalized information because it enables kind of this dynamic integration of knowledge, right?
Mm-hmm.
Also because sort of you're relying on documents that embody some amount of knowledge. You can kind of have some explainability and trust in the answers. And given that it is data dependent, it can also adapt to some real-time context. So there are a lot of benefits, I believe, for using RAG that are hard to find in other inference type frameworks.
Mm-hmm.
But it has a lot of, I feel, drawbacks, but some of which are sort of algorithmic, others are kind of systems oriented. Like you say, sort of privacy is an issue. Also sort of if the corpus of documents is sparse or noisy, RAG doesn't quite work very well. Reflecting on what Rachee was saying, latency is critical end to end. But I feel like it is an important cog in the wheel, that it's not the solution, but it is a part of an overall framework that offers stark trade-offs. But you cannot dismiss it off the bat.
I see. So the speaking of the privacy, right? Would it really be a matter, since we already actually expose a lot of our personalized information to the big tech companies? I mean, this is less technical, but I'd love to understand your opinions.
Privacy is a concern, right? Even when you say that we are exposing a lot of information, and there is a lot of work happening even in general systems, but when we are moving from even those general systems that us, or let's say security researchers, understood well,
Mm-hmm.
how to protect, right? Individual, there is a lot of work, secure systems, building secure systems. But here now what's happening is even how to protect, when particularly talking about agentic workflows, where there are different agents that are working on different requests from different users perhaps, and they're sort of working together. It opens up a whole can of worms. Now we don't even know how to protect one user's data from the other users. On top of that, if we're doing RAG, we're exposing that information without the knowledge of those users, because vector databases are supporting this. But then how do we actually track what requests or what data should only be exposed to those users with certain accesses? All this, the work that we have done in databases, in secure system building research, sort of needs to be revisited when we are doing this kind of agentic workflow. That's actually exciting from the perspective that we're always looking for problems. So in my opinion, yes, the privacy and security actually is important. Even though we are giving out information, it's always going to remain important. How do we make sure that that information is not there are levels, right, of privacy?
Okay, so I think yeah, that's great point. So once we have the comments from the Aditya and Alexey, and I will actually switch back to the some of the specific questions of your talk. So now I'm getting some questions from the audience. Okay,
Alexey, you can go first. I think you were ahead of me.
Yeah, thank you. Yeah, not sure if anyone was paying attention to the raised hand, but anyway. But actually, I think that it is nice to sort of think about this question not in isolation, but together. I think RAG-based systems do expose some privacy concerns, and they also expose some performance concerns. So as I was thinking through this question, it took me a while, apologies, but it sort of reminds me and brings me back to this trade-off between like 5 years ago, everybody was excited about inference, right? And there was this trade-off between offline query materialization and online query processing. So RAG-based systems kind of remind me of online query processing, where you can literally interact with the most up-to-date data. You can retrieve the most up-to-date information, but you do have to have it in some sort of a database. And so in some sense, like there's some database faculty that is actually concerning themselves with optimizing that part, sort of less of a systems problem, more of a database problem. How do you leverage indexing, and how do you leverage sort of database-specific techniques in order to improve the performance of RAG-based systems? As Neeraja also pointed out, I think privacy is going to be a significant concern there, and sort of to address that, maybe an alternative approach to this could be to think about kind of LoRa adapters for the purposes of personalization. And LoRa adapters, again, kind of in this taxonomy that I created in my mind just now, they remind me of more the query materialization approach. Basically, you can materialize all of the personalization information into the LoRa adapter, and you can serve that to that particular user. But it's not going to be, unless you're doing continuous learning, it's not going to be as fast as the RAG-based system. So that's sort of the trade-off. But you do get privacy, because basically everything that had all of the context of the user is going to be specific to just the weights of the LoRa adapter itself.
Aditya?
I just want to build on the first part of Alexey's answer of sort of, the database researchers will focus on performance optimizations, but one could also view that as potentially offering an out for the privacy problem, which is there's been work on private databases, private information retrieval, and the census database offers some amount of anonymity and privacy. So one could imagine that those same solutions, with some reimagining in the vector database context, could also form the basis for privacy.
Okay, that's it. So I will switch gears slightly, and there are a couple of questions for the Neeraja. I will go one by one. Okay, how do you actually decide what layers to drop out when testing LLM?
So yeah, we assumed access to the code, and it was fairly straightforward actually. There is like literally blocks of code that are repeating the same thing. So we don't require users to provide any annotations. We do that. The system does that automatically. We know the architecture. We know we have the code base, but that is lifted from users' buckets.
Okay, got it. So the next question is, can iServe change the strategy dynamically if availability of GPU changes? If that actually leads to the reduction of latency performance or numbers?
The way it works is, it's in real time. Queries are coming, models are being registered with the system. So over time, if there are additional resources becoming available, whatever happens next would take the opportunity and will use that benefit to its benefit. But already deployed models, changing that unless there is a need, I don't think that's kind of something you would want to do unless the intents were changing, and then you had to reimagine how you made the placement decisions. But over time, yes, it is dynamically able to make use of changes in resources that are available, changes in models that are serving or not serving inactive. You can take them off, and so on and so forth.
Okay, so I think the question, another question, probably from the same attendee. So where can you learn more about the iServe and how it works? Do you actually have papers available, archive version, or?
Yeah, it's kind of in submission. That's why we said. But yes, it's on archive, and I'm happy to chat more. The students would love to get more feedback and learn. So please reach out. Look me up. There is an email that I respond to.
Okay. If you can actually share the pointer that we can actually share internally too.
Definitely, I'll follow that.
Okay, so we also have one question for Aditya. How does Gemini achieve a 2 million context length? Don't they face the quadratic complexity challenges? I don't think it's not an easy question to answer because we don't know the internals of how they the Google actually architected their data center. But can you try?
I mean, I think many of the things that actually Alexey talked about may be forming the basis for how they handle very large context length. I think some amount of chunk prefill they must be doing. I am also sure there is models that are spread across accelerators, like you were hinting at Myungjin at the beginning with pipeline parallelism. But the high order bit I'll say is that it comes at a huge resource cost, right? The goal of our work has been to see how frugal can we be in making use of resources. But I'm sure Alexey has more to say here.
Yeah, Alexey, can you chime in?
Yeah, great question. So for the attendees, the slides that I uploaded actually do include the second part that I didn't get to. That was sort of my set of backup slides where we talk about long context support enabled by chunk prefills. And so, yeah, as Aditya pointed out, chunk prefills, they have to be done correctly in order for the long context processing to actually be feasible. And then there was a sequence of work that people have attempted in order to support long context. And you correctly pointed out that the challenge there is scaling attention, right? Because you get quadratic compute complexity and linear memory requirement footprints. You also get head of line blocking issues, and you are limited in tensor parallelism because of the high bandwidth requirements of activations. And so typically the TP is only limited to a single node in realistic inference pipelines. Yeah, so basically what we've done, the long story short, you should try to look at our Mnemoscene paper. You can refer to the reference for that in the slides that I shared with the audience. But it's a combination of chunk prefills and sequence pipeline parallelism, as well as clever overlapping of KB cache parallelism with sequence pipeline parallelism. But we don't know what Gemini is doing yet.
Yeah, actually, that's a good disclaimer. I don't think I was just speculating about what Gemini might be doing, but chunk prefill seems like a very natural choice there.
Yep, that makes sense.
So something I wanna add to what Alexey and Aditya was saying is one of the interesting trends in this space, which I'm sure all of us are looking at, is the expansion of the scale-up domain. So think instead of having one 8-accelerator server, you now have a rack that's all high bandwidth. And then suddenly a lot of the tricks of using the bandwidth in there to essentially access memory within the scale-up domain, and then now you get it at a high data rate, which you don't today, again unlocks using these similar tricks, but now almost treating like all the nodes in that high bandwidth domain are basically just one shared resource. And I think those are ideas I imagine will become increasingly relevant as we see the scale-up domain expanding.
So since Rachee, you're on the spot, I actually have a question for you from the audience. What are the cost-related challenges of optical interconnect? Is it going to be much more expensive than the current XView interconnect?
Right. So the thing with the cost argument for any new technology is the following. When you do something at a small scale, it's always expensive. Does not matter what the technology is, it's always expensive. The way we manage to get economies of scale is we do something at large scales. For example, we managed to fabricate ASICs and CPUs and GPUs at a massive scale. And that's what, I mean, no one's saying GPUs are cheap. Let me just say that. But that's what lets us unlock those low costs. So with that said, this new technology, indeed, as of now, the photonic mesh that we were working with, pretty expensive. But you can imagine as the technology becomes more popular, it's more widely adopted, possibly because of research that we do that shows that this is actually going to unlock some end-to-end benefit. You can imagine then again harnessing those economies of scale. But regardless of the technology we talk about, at a small scale, it's going to be expensive.
Yeah, that's a correct answer, I think. So I think this is, I have a few more questions. Probably this is a general comments and for all of us. I'll just read them out. As we see, the memory is one of the major bottlenecks for LLM deployments. What are the advancements being made in a higher capacity memory development? I think this is a little bit hard to answer, but does anyone take a shot?
Go ahead.
No, Alexey, go for it.
Okay, yeah. So I don't think, at least I know. I'll speak for myself. I'm not a hardware expert, but there's obviously this trend that we're seeing with H100s, H200s, actually increasing the HBM memory per chip. But it is helpful, but that's not where we see the bottleneck. Actually, because we can scale out, and also with the low latency, high throughput domains, also expanding, through some other work that was presented today by Rachee, right? This is going to be less of a problem. We can actually get some memory capacity. What we are severely lacking in is memory bandwidth capacity, because a lot of the issues that we're trying to work around with the systems design right now is actually around the fact that memory fetches are slow and autoregressive decode is expensive because it's memory intensive and things like that. And so it is much harder to actually make improvements on that compared to the memory capacity.
Okay. So just to a time check, we are approaching around, the 10:37 a.m. Pacific time. So some of the panels list have some other commitments. So we'll try to wrap up the panel discussion around 10:40 a.m. So let's keeping that in mind. Let me ask a few more questions. What about the power consumption? We talked about the memory constraint. What about power?
Right. So I mean, I think we're already in a world where we've read reports of how one data center may not be enough to train the next large model. Where in the power grid are we going to get enough power to actually fuel this $100 billion investment, or however many billion-dollar investment? And I think one of the things that is critical, at least I think about this quite a bit, is how do we make sure that the accelerators are not idle? How do we kind of try to keep things at high utilization? There are very many ways. I think we all have across the stack thought about this. What can we do at the software layer? What can we do then at the interconnect to kind of make sure that these bottlenecks don't exist? And I think that's going to continue to remain super important as we get these beefier and beefier, more power hungry accelerators out there.
I just want to add to that. I
yeah.
completely agree with you, Rachee, that it's like that exactly resonated with me. Every layer, it's like full stack from interconnects to the applications, models somewhere in between them, and systems, resource management. But I think it's also super important to think across layers, like whatever you call it, co-design or
Right.
not, or at least
Right.
be informed of the other layer. Otherwise, there are optimizations that are kind of distributed, and sometimes they work against each other. And
Right.
this has been the problem overall in systems. But with models now, there is another angle added. Like these are the algorithms. What kind of data do they need? Where do they need? And going from there, talking about not just like these gigantic models, but just like these small agents working together with each other in a workflow. So they need to make sure intermediate, the data is available for the next agent and whatnot. So everything you said also applies to, let's think across layers
Right.
and inform.
Alexey?
Yeah, so I'll make a comment and I'll have to leave now. So basically, I would like to refer the audience to the paper that was published by Microsoft, Azure Systems Research recently, actually in response to this question. It's a really important problem, of course, for the large data center service providers. The paper is called Dynamo LLM, Designing LLM Inference Clusters for Performance and Energy Efficiency. And basically, I'm really excited about this when I first saw it. There for a whole bunch of reasons. Number one, it is stunning how much energy is actually being consumed by the GPUs that are being idle. So somebody pointed out that we really don't want to see GPU idle, and the reason for that actually is because it actually consumes the floor energy consumption by a completely idle set of GPU machines is a lot more than you would expect. I don't have the exact number, but it's very high. And so the question is, what do we do about that? Well, the GPU manufacturers have tried to come up with things like frequency scaling. So we're back to the glory days of frequency scaling in the CPUs, right? We can dig up all of that literature and apply a whole bunch of the same techniques. And also, get together with Aditya and Neeraja and start doing the same scheduling tricks we did a decade ago for heterogeneity aware scheduling. Because some of the GPUs are better at processing prefill, some of the GPUs are better processing at decode. And we can actually disaggregate them. And some of them are going to be more power efficient that way. We can play tricks with GPU frequency and actually make schedulers aware of GPU frequency fluctuations. Now, that only works if and only if the frequency scaling is sufficiently fine-grained. And this is where Aditya and I really share this philosophical approach of injecting liquidity into the trade-off space. Because without fine-grained choices in the trade-off space, you can't really make interesting decisions. And with that in mind, it seems like the NVIDIA has caught on, and with the H200 release, they do have lower activation delays for frequency scaling for the H200 GPUs. And so that really excites me as a system researcher. And I think that there's a lot of opportunity there.
I actually want to build on what Alexey said, and actually very similar answer I was going to give, which is that there is a lot of slack in the system, and by identifying those areas, you can avoid idling of resources. So for example, I think there was this work from actually Musharraf's group that looked at sort of the dependencies among collectives and communication, and they found that there are certain critical paths that essentially form the bottleneck for the end-to-end delay, but not all other paths need to run at the same speed in order to, because anyway you're going to be bottlenecked by that. So what you can do then is to slow down those other paths opportunistically to, on the one hand, save energy, but also not affect overall performance. So such options exist, and now with emerging NVIDIA chipsets making that easier to exploit, it seems like there is enough on the table to extract energy efficiency from existing systems. I feel like obviously there is some bare minimum energy that all of these systems impose because of the kind of computations they have, but there's also a lot of optimizations that can still be done to shave off easily 20-30% savings in terms of energy. So I feel fairly bullish about that direction.
I see. Yeah, I think the power consumption issue and efficiently, learning the LLMs with the power efficiency in mind is the critical path. I think this is really important. All right. Thank you, everyone. I think we can actually wrap up today's event. Thanks a lot for all the attendees, and thanks a lot for our great speakers. I really enjoyed this event. I hope that you enjoyed the event as well.
Thanks
So
for
thank
having
you.
us.
Yeah, thank you for having us.
Right. Yep.
Thanks, everyone. Bye.
Thanks,
Bye.
Bye bye.